let's straight away get to it. Ice cube is about 1 cubic kilometer of ice, naturally forming glacial ice at the South Pole, into which we drilled holes and we deployed photomultiplier tubes contained in pressure vessels along with onboard electronics. And these devices are then called digital optical modules, and we have 5,160 of these digital optical modules in the ice along 86 vertical strings. Each string is about along each string, these domes are placed about 70 meters apart, and the domes are placed between a depth of 1.4 kilometers and 2.8 kilometers roughly. The array is the main principle by which the detector operates is that we detect photons produced at Cherenkov radiation, which is what happens when charged particles go through ice faster than light can go through ice. Now, the energy at which we are sensitive to neutrinos is roughly, it scales with how close you keep the detectors. So most of the array, the 1 kilometer cube volume, is sensitive to neutrinos above 100 GeV. But at the center of the array, we have a region called deep core, where we have 8 strings that are placed much closer together. So along each string, the DOMs are 17 meters apart as opposed to 70 meters along the other strings. And also those PMTs have higher photo detection efficiencies. So we are sensitive to neutrinos about 10 GeV in this central part of the detector. On the surface of the detector, we have, so these colored dots stand for the surface of, the projection of each string. And on the surface, along with each string, we have a station. We have a tank of water in which we have these DOMs, and they sample directly the charged particles coming in from cosmic rays interacting with the upper atmosphere, which I'll tell you about, and that's called iSTOP. So you can think of iSTOP as an air shower array that's comparable to Grapes 3 in Ooty or Hawk in New Mexico. This is, for example, a picture that was taken while the detector was being deployed. The DOMs were placed along these cable assemblies and lowered into a hole that was drilled in the ice using hot water jets. And our detector, the main component of our detector here is the ice. It is so if you measure the absorption length and the effective scattering length of ice as a function of the depth, which we are able to do because we have LEDs on each digital optical module, which can be flashed, and then the arrival time of photons at nearby digital optical modules can be tabulated. And then you can fit that data to obtain the absorption and scattering lengths, respectively. We construct different models of the ice. The measured lengths are shown here. You will see that at the middle of the detector, something like 600 meters deep into the detector, there is a region where both the absorption and scattering lengths become very small. That is, the ice becomes not too transparent and also a very a highly scattering medium. And that is due to the fact that there is a layer of dust in the middle of our detector, which is naturally occurring. We believe it was created maybe 80,000 years ago when during an interglacial period, volcanoes exploded and deposited a lot of dust into the ice. So if you were to fly into the South Pole, this is where the Amundsen-Scott South Pole Station is, which is aligned with the geographic South Pole, and IceCube is just about 1.5 to 2 kilometers off it. This is the outline of IceCube. It wouldn't be visible, but the counting lab itself is visible. Now, IceCube today is operated by a team of about 350 scientists. You'll see about 350 people on the author list. Majority of about half of them are in North America, and the other half are in Europe, Australia, New Zealand, Japan, and South Korea. Since April 2021, TIFR has been an associate member of IceCube. We are in the process of becoming full members. So in the near future, you may see India also in the lighter colors. IceCube today, it's a large multi-purpose detector that's involved in various aspects of astroparticle physics. I will, in this talk, be talking about neutrino astronomy and astrophysics, so about detecting a diffuse astrophysical flux of neutrinos, searching for their sources, about carrying out correlation searches with other detectors, and also with data from other detectors, and also a future planned extension for IceCube. I'll also be talking about using IceCube to study the properties of the neutrino itself. So some particle results that are relevant to particle physics. There is quite a bit of other science being done by IceCube. In particular, the surface array, which I called IceTop, does quite a bit of composition measurements, spectrum measurements, etc. for cosmic rays. We try to measure neutrinos coming from the atmosphere of the sun. We look for a lot of exotic particle physics phenomena from beyond the standard model. Because we are deep in the ice, we are able to measure properties of the ice that I told you about just now. And also we look for dark matter from various kinds of astrophysical sites where they could be annihilating and decaying. I will not be talking about any of this, but I have backup slides on it. If you want, you can ask. You should view neutrino astronomy today within the context of multi-messenger astronomy, which of course we had various discussions about yesterday. The basic idea is that unlike just the visible spectrum, which we were confined to seeing in which we were confined to observing the universe throughout most of history, in the last 100 years or so, we've been able to build detectors that can go to higher energy photons and show us the non-thermal universe, and lower energy photons, which have convinced us that the universe had a beginning, etc. We have also, for roughly around the same period of time, been seeing charged particles coming in from outer space. And that is one of the motivations for why we actually started trying to image the sky in neutrinos. And in the last 10 years, we have these two new messengers, gravitational waves and neutrinos. The advantage of these different these messengers for observing the universe can be plotted in this figure. On the x-axis, you will see the distance out to which you can image the universe. And on the y-axis, you will see the energy of the particle. And because we know that there is this diffuse microwave background, which we believe originates from the Big Bang, we know that photons at energies of about 1 PeV or so cannot travel too far in the universe. They would interact with these background photons and pair produce and thus be attenuated. So at 1 PeV, the distance you can see out into the universe using photons is something like the distance to the center of our galaxy, not more. We cannot see out to cosmological scales. And at higher energies, it does improve in the case of photons, but in the case of charged particles, which anyway do not carry much information because they're charged and there are magnetic fields in the cosmos which deflect their trajectories, they still cannot travel too far because they also would scatter off these background photons from the Big Bang and produce secondary particles, including neutrinos. So these are the limitations of these messengers. However, the neutrino is in some sense the ideal messenger for the non-thermal universe because it's neutral, so it will not be deflected, it can point back. It interacts only weakly, which means that there is no curve like this for neutrinos in this figure. In fact, the entire universe is transparent to neutrinos, more or less, with the only disadvantage being that the cross-sections being of the weak scale, they are very hard to detect. So we need 1 kilometer cube size detector like IceCube to see a few neutrinos. And the primary reason that IceCube was constructed and why we pursue neutrino astronomy is given in this schematic. That is, for a long time, we've been measuring the fluxes and composition of cosmic rays across about 12 to 13 orders of magnitude in energy. And because they're charged, we don't know where they're coming from. But based on energetic considerations, it has long been believed that below the steepening of the spectrum, so up to a PeV energy also, they are all produced within our galaxy, possibly by supernova remnants. And beyond a PeV, so beyond the knee, that they are mostly extragalactic, but these are all based on back of the envelope calculations. There is no way to verify it by looking at cosmic rays themselves, because like I said, their arrival directions do not carry too much information about where they're coming from. What we could look for is signs of these particles being accelerated in these sources, and so gamma rays would be a way to detect these sources, but they suffer from the fact that if you see a source of high energy gamma rays, you do not know for sure if the gamma rays are produced from hadronic processes or leptonic processes. So there is quite a bit of data analysis and subjectivity to it. Whereas unlike charged particles, the neutrinos, they can be produced primarily only through hadronic processes, and they manage to get out of a lot of material in between, which would attenuate gamma rays. So if you see TV or GV gamma rays, neutrinos from a direction, from a source in the sky, it's sort of a smoking gun signature that there are cosmic rays being accelerated there. And so neutrinos can tell us where cosmic rays come from, and that is why neutrino ice cube was built. So if you consider the different trigger windows in which ice cube is being read out, you will see two types of events. So within these images, which are event displays of ice cube, the color stands for whether the photons were seen early within a trigger window or late within a trigger window, with red being for early and blue for late. And the size you see corresponds to how much charge was deposited within a photomultiplier tube. So this signature, you can clearly see, it looks like a track. There is a clear direction you can see reconstruct from it. And we believe this is from a muon. And if it is in the upgoing direction, we know for a fact that because muons cannot travel through the Earth, all the way through the Earth, that it must have come from a charge current interaction of a muon neutrino. And the advantage is that if you reconstruct the direction of the secondary muon, that is a good proxy for the direction of the incoming neutrino to within, at the highest of energies, less than 0.1 degree, sometimes 0.01 degree. So if you can reconstruct this to a good precision, these sort of events are a good vessel for, let's say, a good workhorse for neutrino astronomy, the way we say it. So the disadvantage, of course, is that this interaction vortex often does not, in fact, it is both an advantage and a disadvantage. This interaction vortex does not have to be within the detector as long as we see the muon that is produced. So we have effectively a volume that is much larger than our instrumented volume for this channel of events. But on the other hand, we have no ability to tell its energy. Only a lower limit in terms of how much energy was deposited within our detector can be said. We also see other kinds of events. Here again, the color coding is the same. Red is for early within the trigger window, blue for late, and size is for charge. But as you can see, the distribution of charge and timing within the trigger window is such that there is no obvious directionality to it. At the highest of energies, by exploiting our understanding of the ice, we are often able to reconstruct these events to about 15 degrees in angular resolution. So for those of you, for those of you who are astronomers, you can see that this is clearly not something we would like to use for astronomy. And the advantage, of course, is that if most of this cascade is within our detector, then our detector is a fully active calorimeter. So all flavors of neutrinos interacting by the neutral current interaction, which is mediated by the Z boson, and also electron and tau neutrinos interacting by the charge current interaction will produce a signature like this. It's either an electromagnetic cascade or a hadronic cascade, but our detector is not granular. It's not finely instrumented enough for us to be able to tell the two apart. In both cases, unlike the India-based neutrino observatory, which has a magnetic field inside it, and so can make the muon curve, and then based on the curvature tell you the charge of the muon, and thus whether the primary particle was a neutrino or an antineutrino. In both these cases, IceCube is not really able to tell you whether it was a neutrino or antineutrino, except in the case of one very small exception that I'll tell you later. So just to highlight, this is the kind of events that lead to tracks. They're mediated by W boson. They're called charge current interactions, and the outgoing lepton is a muon. The same interaction in which the outgoing lepton is an electron or a tau leads to a cascade, as well as neutral current interactions where the outgoing lepton is a neutrino itself, and there is a cascade. Now, if you were to look at the track-like events distributed that are seen by IceCube and look at their distribution in the direction in the sky, you would see a distribution like this. In the northern sky, which is the upgoing region, because we are at the south pole, you would see just a flux of events, of track-like events going up, which we believe originates from neutrinos interacting either within the ice or within the bedrock right below the ice. And those neutrinos, the vast majority of them are produced directly in interactions of cosmic rays with the upper atmosphere. On the other hand, in the downgoing region, which is the southern sky, when you're standing at the South Pole, you have a background a similar background that is 6 orders of magnitude higher in rate. And that is by muons that are directly produced in the upper atmosphere. So in the northern sky, the source is muons produced from neutrino interactions. In the southern sky, these are muons that are directly produced in the upper atmosphere and travel all the way from the upper atmosphere to your detector. And so we see about 70 billion of those per year, whereas the muons produced from atmospheric neutrinos, we see only about 80,000 per year. And buried beneath both these backgrounds, you have today a signal of neutrinos at roughly about 10 per year, which we have detected. And detecting that was one of our major results in 2013. It was on the cover of Science. And how we did that analysis is quite interesting. We looked only at trigger windows where a large amount of charge, so about 6,500 photoelectrons of charge, had been deposited within our detector. And then we use the outermost layer of the detector as a veto. So we made sure that we are not looking at events coming in from outside our detector or secondaries produced from interactions happening outside our detector. We are confining ourselves to really neutrino interacting with nucleons in the ice, but the interaction vortex happens within our detector. That is how, and we also were looking at the highest energy of those. And once we did those, once we applied those 2 cuts, we got a distribution of events, which can be seen in this figure with respect to energy. And based on the best theoretical predictions of how many atmospheric neutrinos and atmospheric muons are there, supposed to be there, convolved with Monte Carlos of our detector, Monte Carlo simulations of our detector, we see a clear excess on top of both those background expectations. And to fit the data, you have to invoke an astrophysical component, that is neutrinos that are directly coming in from outer space. And they are, to first approximation, they're distributed isotropically. Now, if you plot their directions in the sky and you do a likelihood analysis for clustering, you see that you don't, you may see some hotspots which suggest that you see a significant clustering in some direction, but you're also carrying out this likelihood analysis at every point in the sky on a grid. And once you account for that look elsewhere effect, there is no statistically significant clustering. So this is not statistically significant. The arrival direction distribution of these events is consistent with isotropy. And the main reason for that is that the majority of these events, at least three out of every 4 events, are cascades. So they have angular resolutions of 15 or 20 degrees or worse, and not tracks which have angular resolutions less than a degree. Just to make it explicit how we identified these events, we have plotted the charge deposited by IceCube charge deposited by each event within the IceCube detector along 2 axes. This is the total charge within the detector, and this is the charge within the outermost layer. So you're looking at the highest end of this along this axis and the lowest end along this axis, and you apply this cut, and these are your events of interest. Now, we confirmed the presence of this astrophysical flux of neutrinos today with more than 7.5 years of data public, and we have 10 years of data which we are analyzing internally at way more than 6 sigma. But we have also confirmed the same flux in many other channels. So not just in contained events, but also through going tracks. So in an independent sample of events in which we did not use the outermost layer of the detector as a veto, and we look primarily at tracks, there again, you see a flux excess at the highest of energies, which cannot be explained by any of the known backgrounds. In non-contained cascades, 6 years of data, again, you see an excess at the highest of energies, which cannot be explained by any of the known backgrounds. And you can fit a spectral index to each of these individual fluxes and a normalization. And on that, in this parameter space, you see that all of these analyses are compatible to each other within 2 sigma or so. There was a brief period earlier where there was something like 2.5 sigma tension between some of these channels, but as more data came in, the tensions have reduced and all channels are compatible with each other. We are seeing an isotropic flux of neutrino with roughly this normalization and a spectral index between 2 and 3. So 2.5 to 3. This is the diffuse flux of neutrinos we are seeing. Now, as I showed you, if you just plot their directions in the sky, we don't really see any obvious sign that they're coming from a particular source or that they're clustered around any specific direction in the sky. So starting in 2016, what we did was we started trying to alert the community as soon as we see one of these events. So when we first detected these events, to reconstruct them, to infer the direction of the incoming neutrino, the energy of the incoming neutrino from the distribution of photons we see within our detector, involved algorithms that would take days to run on a computer. And we decided to make a real-time alert system. We had to speed up much of these algorithms, and I was quite involved in that process. Thanks to the use of splines and multi-step method, wherein you initially come up with a very coarse estimate for the direction and energy, and then you follow up later with a more accurate estimate. We have been able to, since 2017 beginning, send out alerts within 17 seconds of the detector being triggered. And these alerts go out into astronomers' telegrams, gamma ray coordinate networks, and also something called the Astrophysical Multi-Messenger Observatory Network, which is a real-time data sharing agreement. And they go out to different telescopes which have subscribed to our alert stream. And since 2016, we have been sending these alerts. And so far, there have been 60 alerts or so. In 2017, September, I think this was the 11th or 10th alert we were sending out. The first 9 or 10 alerts we sent out and nothing particularly interesting happened. But we sent out an alert in 2017, September, and within 3 or 4 days, we found a sequence of astronomers' telegrams and GCNs from other telescopes, mainly MAGIC, the Imaging Atmospheric Cherenkov Telescope, and also Fermi, the space-based gamma ray telescope, saying that they see a blazar which is within the contour of our the directional reconstruction of the single event, which had deposited about 290 TeV within our detector. And they found that this blazar was in a state of heightened gamma ray activity. It was emitting about 10 times as many gamma rays as usual at both TeV and GeV energies compared to what you would expect of its average long-term time average. And so this is, I forget what constellation this is, but the source is right below its arm. And if you look at the contours, you can see the ice cube 50% contour here, in gray, and in red you'll see the 90% contour. And here already you can get a idea of how good neutrino astronomy is compared to other messengers. It's fundamentally limited by the kinematic angle between the incoming neutrino and muon. So we can never hope to have the angular resolution that MAGIC or Fermi does. But the angular resolution, nevertheless, is good enough, for example, to tell us that it did not come from this source, which is another blazar that was within, it is somewhat close to this event. But because our contours here, we know it didn't come from this source. Now, so we at the time of sending out this alert, we had already sent out 9 or 10 alerts, and there were different, follow-up campaigns, which was really not in an automated way. It was human beings looking at these alerts and deciding whether to point their telescopes in those directions, in different directions. And we were not sure if this was if this was actually statistically significant. So a long series of exercises were undertaken to evaluate if accounting for the look elsewhere effect of all the alerts sent out so far, etc. This is possibly a statistical fluctuation. And after the most conservative methods of statistical methods were employed, we still believe that this was statistically significant at about 3 sigma level, which, if you're a particle physicist, is not really something to be excited by. But that gives us some reason to think of this direction in the sky corresponding to the source as special. So we kind of went back, and looked at our archival data in that direction and did a time-dependent likelihood analysis. And in this case, because we have no reason to privilege other directions in the sky to the extent we are privileging this direction, there is no look elsewhere effect. And in this analysis, we see a 3.5 sigma excess between 2014 and 2015, an excess of 13 events compared to the background. And this is also a time-dependent signal. Here you can see that its spectral index is about 2.2, so it's quite a hard spectrum. That is, there is relatively more events at higher energies. And the key thing to realize is that this was a standalone. This was an analysis of our archival data. And in this period, there is no other multi-messenger counterpart, or there is no enhanced gamma ray emission from the source. At least it has not been detected. For example, the source was within the field of view of integral, and some IACTs were pointed at them, and there are upper limits, and the upper limits are higher than they were in the 2017 period. So these two separate analyses, which do not have the same signal hypothesis and thus cannot be combined to produce 1.5 sigma. One analysis looks for the probability that a gamma ray enhanced activity as seen in IACTs and Fermi is correlated with a single neutrino event. And the other analysis shows a time-dependent clustering in the same direction, but with no corresponding enhanced flux in any other messengers. Both independently give slightly above 3 sigma, 3 to 3.5 sigma confidence that this is this is the first extragalactic source of TeV neutrinos. At the time of this identification, there were many questions. So why is, for example, so at the time we saw this event from this blazar, its redshift was not known. But the excitement created by these follow-up efforts led to people pointing a spectrograph in the direction and measuring its redshift, and it turned out to be a redshift of 0.3, slightly higher than 0.3, 0.33 or something, which you can see is clearly cosmological. It's very far away, 4 billion light years or so. So the first question is, why is it? And we see objects that are blazars, which are active galactic nuclei with their jets pointing towards us. Many of them which are much closer than this 4 billion light years. So one of the first questions that rose was, why do we not see a comparable neutrino emission from the closer blazars? And this question is at least not that big a puzzle anymore, because we do see one more source. And so, blazars became a very exciting candidate to as potential sources of high energy neutrinos. So this is what you think of as a multi-messenger spectral energy distribution. All the photon data is tabulated here, and the neutrino data of the single event, depending upon what period of the detector you consider, is also tabulated here. We have looked for correlations between these high energy neutrinos within our contained sample of tracks and cascades. And for example, ultra high energy cosmic rays seen by Pierre-Auger Observatory and Telescope Array. And we do not see any statistically significant correlation. They appear to be completely uncorrelated with each other. And that is not surprising because, like I said, the ultra energy cosmic rays can travel a few hundred megaparsecs at best due to their interaction with background photons, whereas neutrino horizon is essentially infinite. So we do not expect any correlation at more than a percentage level between these two messengers. We have looked for neutrinos coming directly from these neutrinos produced directly from these pion decays in these interactions, with because of ultra high energy cosmic rays interacting with background photons. The optimistic models predict a flux that is above our sensitivity, but we have not detected anything. And what this suggests is that the optimistic models are not true, and the optimistic models are based on the assumption that the highest energy cosmic rays are all protons. And we have multiple independent lines of evidence slowly starting to suggest that the highest energy cosmic rays are not likely to be protons. In fact, they are dominated by heavier nuclei. Of particular interest to you might be the fact that we have also been looking for correlations between these high energy events we see and also high energy events in different channels within our detector with gravitational waves. So every time the LIGO-Virgo collaboration sends out a gravitational wave alert, we carry out a fast follow-up analysis, seeing if one of our events happen to be coincident with them. So far, there has been no coincidence. Even in the case of the neutron star merger, which had an electromagnetic counterpart, even though the paper was published saying it was the first event that was observed from all 5 continents, and we were one of the detectors in Antarctica that was technically looking for this. We saw no events. We have only an upper limit, and that is current models of this neutron star merger, or current observations of it, show that the jet that was produced as a result of that event was not pointed towards us. It was, I think, between 11 and 17 degrees or so, pointed away from the line of sight. If it was within less than 4 degrees, perhaps ice cube would have been sensitive to it, depending upon different models, but it was not aligned that closely, and as a result, the ice cube upper limits are much higher than the model predictions. But in the future, if similar events keep happening, and luckily one of the jets happen to be aligned with our detector, we have a reasonable chance of seeing them. But yeah, we have been carrying out correlation analyses with all the different gravitational wave events that get announced. And you can see the banana plots in the sky corresponding to each of the gravitational waves. And in green, you can see the neutrinos, and you can see that there is no directional correlation. The neutrinos we see within the same time window, which are at the highest of energies and have a high likelihood of being astrophysical, are nevertheless not directionally correlated with the gravitational waves. So now I'll talk about the search for point sources of neutrinos, which was originally the kind of analysis that we were carrying out before we used this veto-based analysis, which detected the diffuse flux of neutrinos. So this was the kind of analysis that was conceived of IceCube doing when IceCube was designed. And the idea is that you don't use a veto, you don't have an energy threshold either, but you look only for things which are clearly tracks within your detector. So if you isolate only tracks, you get a sample which in the northern sky is dominated by muons produced from atmospheric neutrinos, and in the southern sky is dominated by atmospheric muons directly. And those are expected to be distributed uniformly within each declination band. But any point source neutrinos coming from outer space, so any neutrinos coming from a point source in outer space, they should be directionally clustered. So if you carry out a likelihood analysis looking for statistically significant clustering within these randomly distributed samples of tracks, And if you detect statistically significant clustering, you can think of it as a detection of a point source. Another ingredient property of each event that can help in this is that most theoretical understanding of how neutrinos are emitted and how charged particles are accelerated in sources predict that neutrinos coming directly from outer space should have a harder spectrum. That is, there should be relatively more at higher energy than lower energies compared to, for example, the atmospheric neutrino and muon backgrounds. And the objective of this is to find the signal that's buried here. It's the lower energy neutrinos we are looking for. The signal at the highest of energies has, which is diffuse and in which finding point sources require multi-messenger correlations have already been explored in the previous analysis that I told you about. And with this sample of events, as you can see, you get, so okay, I'm using the same plot twice. I'm sorry about this. The angular resolution gets as good as about 0.25 degrees at the highest of energies. And there are about 600,000 tracks in about 7 years of data, which are now public and which you can access and analyze yourself. And so we took one of these samples of data. This is with our internal latest 10 years of data, and we carried out an analysis. So what this analysis does is it looks at each point in the sky on a grid of 0.1 degree by 0.1 degree and maximizes a point source likelihood, looking for statistically significant clustering. And using Wilks' theorem, we can quantify the p-value of by which each point is not compatible with the background-only hypothesis. You see these very small p-values in the northern sky and southern sky at the hottest of spots, which would suggest that we have found point sources. But the issue is that there is a large look elsewhere effect corresponding to, or which is called a trial factor, depending upon whether you're a Bayesian or frequentist, which is associated with the fact that you have looked at every point in the sky. So there is a large penalty that you have to impose upon yourself because you're doing a large number of trials. And once you impose that penalty for yourself, so once you ask in random skies, how often am I likely to see the hottest spot, hotter than what we have observed so far, once you account for those trials, the p-values are about 0.75 and 0.1 roughly. And as you can see, those are large enough values of p-values and they're not statistically significant. So a simple analysis of the sky that we originally thought of for IceCube to do to this day, because of the large look elsewhere effect associated with scanning every point in the sky, does not give us a statistically significant detection of a source. But we have no reason to privilege every point in the sky equally, other than in perhaps our most democratic analysis. We know from gamma ray astronomy, especially from IACTs, that a very large number of sources in the sky emit high energy gamma rays, and they are more likely to also emit neutrinos. So we can look in promising directions in the sky as identified by other observatories. And if you do that with the same analysis I showed you earlier, you are basically reducing your total trial factor by to just 120. So if you look at just 120 promising sources, for example. So you first construct a catalog based on TeV and GeV gamma ray emitters, based on some principles that you believe make them promising neutrino candidates, and then you carry out the search only in those directions. And if you do that, you see a few hotspots in the northern sky, and even after you account for the 120 trials associated with looking in 120 directions in the sky, one of these hotspots is still statistically significant at about 4.2 sigma, which is quite exciting for us astroparticle physicists, though it's still not at the 5 sigma threshold. And if you look at the distribution of events from that direction, what you will see is that if it was just background, the distribution of events at different angles from that, the direction of that source should have been this orange, but you see a clear axis from the direction of that source, and that is NGC1068. Now, if you look at the normalization of this flux and the spectral index, here you will see that the source is very soft. Its spectrum is something like e raised to minus 3.3, 3.2. So it has relatively more neutrinos at lower energies compared to higher energies. So this, for example, is once again a multi-messenger SED of this source, NGC1068. Yeah, a few things need to be said. The source NGC1068, unlike the TXS source I told you earlier, is much closer. I think it's within 30 megaparsecs or so. So it's really within our local cosmic neighborhood. MAGIC, the Imaging Atmospheric Cherenkov Telescope, had already measured the neutrino flux from the source. Sorry, not the neutrino flux, the gamma ray flux from the source. And based on the gamma ray flux and based on the kind of physics that goes into models that are used to explain multi-messenger data, they had predicted that the neutrino flux from the source would be about a factor of 100 smaller than what we eventually ended up measuring. So that should be a cautionary tale against some of the theoretical calculations that are being done in this field. And the reason, of course, is that, the reason that is now being said is that the reason the neutrino flux turned out to be much larger than the gamma ray flux is that the source is dust obscured. So there are gamma rays being produced, but they're being attenuated by a dust that's between our detector and where the gamma rays are being produced. And as a result, the gamma ray flux is suppressed, but the neutrino flux turned out to be much larger than expected because of that. So every time we produce a flux measurement for any source, you will occasionally find models such as this one by Murase, which claim to overlap with our flux measurement and thus explain the data. But if you look at the number of parameters involved in these models, what kind of physical assumptions they make, I'm not really sure what is the point of this kind of modeling. One can always fit data, but you don't really seem to be learning much from the process. This is the flux that has been measured, the diffuse astrophysical flux. These are the two sources. This is the source that I told you about earlier, the blazar at cosmological distance, and this is the nearby dust obscured blazar. And as you can see, both these sources together contribute a flux that is about 10% of the total diffuse flux or so. The remaining 90%, the sources responsible for that still remain to be discovered. With these track-dominated events, we have carried out stacking searches. For example, Fritz Zwicky has had an argument, going back 100 years that supernovae provide most of the energy for galactic cosmic rays, and then Fermi came up with a mechanism for how the shells of these supernovae, the shocks at those shells can accelerate cosmic rays. So for a long time, we still believe that galactic supernova remnants are great sites for cosmic ray acceleration. We have carried out stacking searches looking for them, but so far we have not found any statistically significant clustering or even excess from directions of different known supernova remnants in the sky. Even when you add them up, there are some very weak hints, for example, from supernova remnants in the Cygnus region of the galaxy. But the main reason is that much of the galaxy is in the southern sky for IceCube, where because of this muon background, our sensitivity is not as good as in the northern sky. A neutrino telescope really is best when it is looking through the Earth. The Earth can kind of block out all the atmospheric muons, and then you only have the irreducible background of atmospheric neutrinos to worry about. So the fact that we have not seen any excess from supernova remnants allows us to set constraints on very optimistic models. Some of the more optimistic models have been completely excluded, and some of the more pessimistic models are going to be within our sensitivity range in the next 5 or 6 years. So this is quite promising, but I think we should look out for analysis from Northern Hemisphere neutrino telescopes like KM3NET or the proposed Pacific Ocean neutrino experiment or any of these upcoming ones. We have looked for a flux of neutrinos from the galactic disk, the galactic diffuse component, which follows, for example, the Fermi pion decay map. And we have once again not detected any statistically significant excess from the direction of the galactic disk that follows this template. In fact, realistic models of neutrino flux production from the galactic diffuse the realistic models of diffuse galactic cosmic rays are anyway beneath our sensitivity. We have looked for correlations with gamma ray bursts, but with 6 or 7 years of data. And the most optimistic models of how gamma ray bursts accelerate cosmic rays are now excluded because of the fact that we see no correlations. And this rules out gamma ray bursts as the dominant sources of ultra energy cosmic rays. We have looked for correlations between sub-threshold warm spots we see within our detector, that is in the point source search points in the sky where you see something like a 2 to 3 sigma excess. And we have looked for correlations with local structure of matter, and we don't see any excess there, but unless if with promising source candidates like low luminosity AGNs or starburst galaxies, this is expected to give us a correlation only with the next generation IceCube detector. I see that I'm already on 45 minutes, so I'm going to skip the particle physics part of this talk because, this is also a neutron star conference, so I don't think it is of interest to you. I will just skip directly to the summary, which is that IceCube has discovered a diffuse flux of high-energy astrophysical neutrinos, and neutrino astronomy is at a stage comparable to what gamma ray astronomy was in the 70s. What I mean is we have a diffuse flux, we have a few sources. Our sensitivity to point sources now will improve only as 1 by square root of t. We have already been running for about 10 years, since 2000, or so 12 years now, since 2011 to 2023. And so if we run for 24 years, that is next 12 years, our sensitivity will just improve by maybe 40%. So if you want to image the sky in neutrinos properly, we need a much bigger detector. And for that, we have envisioned what is called the IceCube Gen 2 detector. So that is basically going to be this blue region. The red region is the existing IceCube detector, and the green region is the deep core infill. So IceCube will be to IceCube Gen 2 what deep core is to IceCube. And we are going to make a detector that is about 10 times the instrumented volume of IceCube without making it 10 times as expensive, by just placing these digital optical modules in the eyes further apart and also putting more strings. So instead of 86 strings, we'll have 120 new strings. We'll have 80 DOMs per string. And the detector is going to have about 10 times the volume of IceCube. The threshold will be larger. It will be about, instead of 100 GeV, about 10 TeV. But that's okay because all the astrophysical neutrinos we have seen are about 10 TeV or so. For the first time, this detector will also have a large radio array component. So just like Cherenkov radiation is produced by these interactions, they also produce radio between 100 megahertz and 500 megahertz, if I'm not mistaken. And that can be detected using a phased array, about 200 stations, which was tried out. This technique has been, that it can work, has been validated by something called Ascarian radio array. So if this is what is Gen 2, Gen 2 is going to be a small, Gen 2 optical array is going to be a small part of a much bigger array of about 200 hybrid radio stations, which will have antenna deployed into the eyes like this. And that, so yeah, IceCube Gen 2 is going to be an optical radio, optical plus radio array with stations like this. And the surface array of IceCube, which I called iStop, will also have scintillator-based detectors that will serve as a proxy for the in-eyes array, and we can, in principle, extend it for as large a solid angle as possible and try to get a veto over the as large a solid angle of the sky as possible. So this is something we are exploring from the TIFR side. My postdoc Manisha has already been working on it. The cables required for IceCube Gen 2 are we may be building those in India. These are cables that are 3 kilometers deep and will have to survive for hundreds of years going all the way to the bottom of the ice, where the temperature will be minus 70 degrees and pressure will be as high as 700 bar. So these are some very special cables we'll have to make. And also IceCube Gen 2 will have very different types of optical modules. These include, for example, so for the IceCube, the optical module had a single photomultiplier tube that was pointing downwards. For IceCube Gen 2, we'll have optical modules with either 2 photomultiplier tubes pointing in both directions, or 24 photomultiplier tubes within a DOM, which have smaller photocathode area. And the point is that you are not only just sensitive to the fact that an optical module has seen photons, you're also sensitive in which direction that photon came from, which can be useful information for reconstruction. So those ideas are being explored. And I think I will stop my talk now since there are only 10 minutes left for discussion. That's it. We have done some astronomy with neutrinos, and we need a bigger detector to continue to do better astronomy with neutrinos.
Yeah.
Thank you.
So thank you, Ramesh, for a very nice talk. And let me just add that IceCube has made all this data publicly available. It's one of the very few, or maybe the only high energy physics experiment which has done it. So any of you can analyze the data and so on and so forth. So I open the floor to questions. So any questions? Students, yeah. Avinash, 1 second. Let me just come to you.
Hi, I have a question. Can this IceCube detector be used as a particle detector, which can detect other particles?
Sure. So there are, IceCube is very much a particle detector. In fact, so for example, just to give you one example of some papers you'll find if you go on Spires and search for papers written by IceCube, is that wow, I seem to have a lot of slides. Let me just scroll back to the, I showed you these. Yeah. So you can look, for example, in some supersymmetric scenarios, there are predictions of what is called a trident. So you will have one vertex and then 3 tracks coming out of it due to 3 muons that are produced simultaneously. You can look for those. We have so far not seen any. There is also a standard model expectation for it, but that is extremely small in the sense for a detector our size, it's you should never see it on human timescales. And searching for such events have allowed us to set constraints on operators corresponding to that. In SUSY, we have some triggers which don't look at less than microsecond timescales, but look for example, magnetic monopoles. So if magnetic monopoles go through our detector, they will lead to like a prolonged period of they'll cause this proton decay. This is one of the hypotheses. We have looked for that. We have not seen magnetic monopoles, so we have stringent limits on magnetic monopoles. We have a whole bunch of dark matter searches, basically the same way gamma ray telescopes look for dark matter by looking at different targets in the sky, which could be promising sources where dark matter is annihilating. We look for neutrinos from the same direction. We don't see anything. We set constraints on neutrinos also. We set constraints on the dark matter annihilation, thermally average annihilation cross-section. IceCube has a wide array of other searches for other particles. We have recently, for example, detected the tau neutrino, which I did not speak about again because I had actually some slides on it because I thought it'll take me 15 minutes to get there, but I kind of distinguish between the neutrino astronomy and the particle physics side of it because they are of interest to different communities. But in principle, if you have an understanding of our triggers, which are very simple compared to any LHC detector, and you have an understanding of particle physics, you can set limits on almost any kind of interactions with our detector.
I have one more question. The radio antennas that you have talked about,
yes.
Are they placed above the surface or inside the ice, or what is the kind of mechanism?
So they go about 100 meters into the ice, right? So yeah, these were the particle physics slides we have seen. For example, the Glashow resonance. Just answering your previous question in a little bit more detail. This is a particle physics process that you will never be able to create a neutrino beam on Earth to verify that it exists, but we are about 100:1 odds confidence that it exists. We have confirmed the standard model prediction for the neutrino and nucleon cross-section, though there's quite a bit of circular logic involved in that. We have confirmed the standard model prediction for what is called inelasticity in each interaction, how much energy goes into. But yeah, let's get to the radio question that you asked. These detectors are placed about 100 meters. So you place them at the surface, and as well as the electronics and the readouts, etc. And then you place the dipole antennas along strings about 100 meters into the ice. These contain dipole antennas which have both horizontal, which are oriented in such a way they're sensitive to both horizontal polarization and vertical polarization. And the reason for that is when these interactions happen in ice, the radio, you will get both the direct radio emission and also the radio emission that's reflected off the top surface of the ice. And once it gets reflected, the polarization gets rotated. Sorry, I know very little about radio detectors or astronomy, but that is how I understand it. And how these radio emission is produced itself, it's called the Ascarian effect. So you can think of it sort of like the radio equivalent of the Cherenkov effect, but there's also the fact that the shower that's produced in the ice, it has an excess of negative charge and less of positive charge, because the positrons will annihilate much faster than the electrons in those showers. So yeah, there's quite a bit of, but just to also mention the existing array, which is the prototype based on which this is going to be deployed, the Ascarian radio array. They've only operated about, I think, 20 of these stations, or maybe less than that. I don't know the details. And they have so far not seen any promising neutrino events, but all technology has been validated, and we are hopeful that, the radio array will give us useful information, especially when used in conjunction with the optical array. That's how we're looking at it right now.
Yeah, one more small question. How are the sensitivities compared to all these different methods? Are they equally sensitive, or one is much preferred than other?
Okay, I may have a backup slide on it, but if not, I'm going to keep answering any. So radio, the method is really like you get a radio pulse that is sensitive enough, that is strong enough for us to start inferring neutrino properties, only if the neutrino energy is above a few PeV. Whereas, like I said, IceCube is, sorry, I don't have the backup slide on it, but okay. IceCube is sensitive to neutrinos about 10 GeV if you go down to deep core, 100 GeV if you go down to, if you consider the rest of the array. And then because the flux is steeply falling off, we have seen events as high. The highest energy events we have seen are a few PeV in energy. And that few PeV happens to be the lowest energy at which the radio array can operate. So we have like 1 decade of energy where the two arrays will overlap in energy. But beyond that, the optical array is not expected to have sufficient sensitivity. Gen 2 optical array will go up to maybe 50 PeV or so in energy, because the flux is even lower, but our effective volume is larger. But the radio array's sensitivity starts at that point.
They're like different parts of a spectrum.
Yes, exactly. Yeah, they sample different parts of the spectrum.
So thank you.
Okay, Maura?
The radio, you get like better localization, or yeah, I'm just wondering what the radio gives you. Like, can you get better localization, better measurements of like what specific properties?
So like I said, it's in an energy range much higher than optical, and is much cheaper to build. So that is one of the reasons we are putting in. The other thing is that it, with a very sparsely instrumented optical array, we may not be able to localize the vertex that accurately. It really depends on how well we model the ice. So IceCube keeps improving our understanding of the ice. And so all our detector properties have been slowly getting better as we do better calibration. But we are hopeful that the radio, apart from just extending our energy range for cheaper to much above PeV energies, will also give us better resolution for the interaction vertex, etc.
I'll just add, I think in US, such a search has also been done with the Goldstone array. I think someone from UCLA had led that, I think maybe about 15 years ago. There's also the Anita experiment also, right, which looks for something similar. And just to answer Avinash's question, right, I think many of these muon detected, IceCube detects cosmic ray muons also. So you can do things like sidereal anisotropies, Compton Ketting effect. And I think many of the previous detectors also found the shadow of the moon, the fact that moon blocks some of the cosmic rays. I think IceCube has done something like that, right?
Yeah, so we use that to validate our pointing. All of our Monte Carlo studies can only, this is the moon shadow analysis. All of our Monte Carlo analysis can only tell us how good our relative pointing is. To be sure, our absolute pointing is, is good. We look and make sure that we are seeing the moon where it's supposed to be with the kind of deflections we are supposed to be seeing. We saw the moon shadow within our detector. It's a standard practice for all air shower arrays or things that are sensitive to secondaries produced in air showers to make sure you're seeing the moon shadow as a way of validating your pointing.
Any other questions? Yeah, Neil.
How is IceCube Gen 2 going to work with the cubic kilometer telescope coming up in Europe?
I mean, it's not going to, we are going to have a real-time alert system, which is not really relevant because, like I said, IceCube the Earth is essentially transparent to neutrinos at above PeV energy. So you don't need to point your detector. You don't need to change trigger conditions, nothing. You can just keep operating. But already the smaller version of KM3net called Antares, we have combined our two detectors and done point source analysis, but Antares has only a instrumented volume comparable to deep core. So it's a much smaller detector. KM3net will have an instrumented volume that's comparable to IceCube Gen 2, and it is in the northern hemisphere, so it will be more sensitive to the southern sky, which is where much of the galaxy is. So I am hopeful that KM3net and also the Pacific Ocean neutrino experiment, and also the Chinese are proposing something in the South China Sea called Trident. I am hopeful all of these together will be able to, image the galaxy in neutrinos, which IceCube has had very little success with because we are more sensitive to the northern sky, where much of the galaxy is not there. But you can think of them as quite independent detectors. There's not much in common. I mean, water is a different medium from ice. Water absorbs more photons but scatters less. But then water is not solid, so that your detectors move around. There are a lot of issues. But in terms of science, you can combine the data from the two and use them as a combined neutrino telescope if required.
Okay, so Ramesh, one more question. Maybe you can give a quick answer since we are just 1 minute past time. So there also, I read claims about neutrinos, IceCube detecting neutrinos from tidal disruption events. You didn't mention that in your talk. Can you say 1 or 2 sentences about that?
This claim is by an independent group based on some of the alerts we have sent out. Right, it's not something IceCube has published. We are still discussing within our collaboration what exactly the statistical significance of that is, because the moment we send out alerts, whether those alerts get followed up, and so effectively in frequentist terms, whether a trial actually happens is dependent on a lot of human considerations, whether another observatory is choosing to follow up our alerts, etc. So I don't think there's consensus within the collaboration on what the statistical significance of that is, but it's possible. We're not against other people in the community doing this sort of searches and speculating. That we plan to have an opinion from the side of the collaboration soon, but it'll take a little bit of time because consensus needs to be built.
Okay, Gopu.
A very nice talk, Ramesh. So this is about KM3net and IceCube 2 working together. So essentially, that should be able to kind of confirm or kind of put it in firm footing the SEDs, whether leptonic or hadronic, right? I mean, so that because you get lots of galaxies from the southern hemisphere together with the northern one. So the SED explanation whether the high energy cannot really dominated by the leptonic model, right? So
I mean, in some sense, the very fact that neutrinos are being produced tell us that there are at least some hadrons there, right? I am interested in that sort of inferences rather than these. So I read through some of the leptonic models that were published after the leptohadronic models, which have a parameter which like values of that parameter determine whether it's primarily leptonic or primarily hadronic. And I don't know, these models are they're very reductive, and they're basically spherical chickens in a vacuum. And I'm not sure what you learn by. I would, I would say that the fact that we've seen neutrinos from some sources suggests hadrons are being accelerated there. The question of whether it is primarily mostly hadrons there, mostly leptons there, that depends on how much complexity you're willing to assign to those sources. And I don't think these sort of reductive parametric models capture them. And in fact, the argument I made about Magic's prediction that we should see one in 100, like a factor of 100 suppressed neutrino flux that source compared to what we saw is sort of, it's the kind of pitfall of this sort of modeling of astrophysical sources, right?
I agree. Just one small follow-up. PWN. So why are we looking at pulsar wind nebula? I thought if there are neutrinos produced, it's already gone, right?
So pulsar wind nebulae, this was from the backup slides, I guess. So
You should kind of scan.
Yeah, sorry, I was looking for a backup slide. It was not meant to be it's something I did for my PhD. I would agree with your theoretical argument that it is not well motivated, but it has also been my experience in science that looking for a search that is not theoretically well motivated and showing there is a correlation is some of the ways we make progress. We did not see an excess, so nothing surprising happened. But I saw there are quite a few models predicting, for example, by a Polish guy, Bednarek, wherein you have the pulsar accelerating cosmic rays to PV energies, and then the wind nebula around it acts as a beam dump for these cosmic rays, and you get neutrinos from that. So there are all sorts of models that claim pulsar wind nebulae could produce neutrinos, but empirically we have not seen anything. So that's my view of the subject.
Okay, thank you very much.
Okay, so let's wind up. I think next talk is by Chandrakant Mishra. So let's thank Ramesh for a very nice talk. I'll just say one more thing about Ramesh. In addition to all this great work he's doing in neutrino astrophysics and all that, Ramesh also has a parallel career in the field of cosmology, where he is one of the few persons who has a chutzpah to challenge a Nobel Prize winning result. So I urge everyone to just pick his brains on everything he does. Okay, so.
Thanks for your kind words, and thanks a lot for this invitation. It was my pleasure.
The next talk is by Chandrakant Mishra. And this is is going to give the talk in person. Yeah, so just give 2-3 minutes. If anyone has more questions which can be answered without a slide, anyone else? Without the slides, we can just. Yeah, please, which can be answered without the slides while Chandrakant is setting up. Ramesh, are you still there, right?
I'm still here, don't worry.
Okay. Anyone has questions while Chandrakant is setting up? Okay. So thank you, Ramesh. So maybe there might be more questions during the discussion after this talk. So, okay. So next we have Chandrakant Mishra from, I guess, across the town, and he's going to talk about measuring neutron star tides using gravitational waves. So Chandrakant, please take it away. Really good.
Am I audible through this? Yeah, okay, okay. Okay, good morning, everyone. Let me first thank the organizers for giving me this opportunity to discuss very little that I know of this subject. My expertise ends at considering neutron stars as point particles. So I will be directing the questions related to the macroscopic properties of neutron stars to the organizers and the audience. But I'll try to highlight a few things that the collaboration has found, and I'm part of that collaboration. And also a quick analysis that we recently did by using some of these results. Now, what we have on screen is essentially a snapshot from a simulation. It's not a full GR MSD simulation, but rather a GR simulation and a matter simulation separately. So on the right, you have how the matter density evolves as the two neutron stars come closer and merge, and on the left you have the emission of gravitational wave from the binary system. Now, sorry. Now this is the publication that reported the discovery of the first binary neutron star merger. And what we see in the figure is essentially the track that a gravitational wave merger event leaves in the detector data. It's a signal that ramps up both in amplitude and frequency. On the y-axis, the frequency have been plotted, while the normalized energy represent the amplitude of the signal that is there, and it increases from blue to yellow here. Okay. Just a couple of things to highlight here. While I'm sure, the audience here knows about this event much more than I know, but I just wanted to highlight a couple of things. So this was a signal with significant strength. We call it signal to noise ratio of 32, which is quite high, thanks to the closeness of this event. So this event was detected at 40 megaparsecs, closest gravitational wave event we have detected so far, including another binary neutron star system. And if I'm not wrong, this is also the closest short GRV that we have detected. So due to that, we have very high SNR event, and that helps us exploring the properties of this event in great length. And the second thing is that I want to highlight is the statistical significance of this event, which is less than 1 in 10 power 5 years. Okay, it just means that there is 1 in 10 power 5 chance that only 1 in 10 power 5 chance that it can be a false alarm and not a real event. So statistically quite significant event. Now, again, as I said that most of the audience might know the properties, but I'll just walk us through some of the aspect which may be useful in discussing what I want to present here. And one of the things that I want to highlight here is this is the chirp mass. It is a combination of the component masses, a special combination of component masses. And this is the best measured parameter for any gravitational wave event, not just this event, but any gravitational wave event. And this you can see from the error bars, which are very low. This is our best measured parameter. Now, when one comes to constraining the component masses, it's not as accurate as the chirp mass. And the reason being that the component masses are correlated with their spins. And that leads to the measurement not so good, not at the same level as the chirp mass parameter. And also it's the chirp mass, the mass ratio information, which leads to the constraining of the component masses, also is subdominant, as we'll see in the structure of the waveforms. Okay, so that is one point. And this is indicated in this plot. So on top, we have the constraints on the two component masses. And another thing that I wanted to point out is here, the results have been presented for two sort of situations. One is when we assume that the involved neutron stars do have small spins, and we limit the value of this small spins to be 0.05. And the reason for choosing this configuration is essentially the observed double neutron star systems. If you take an example of the most relativistic double neutron star system that we have observed so far, or that is going to merge within the Hubble time, if you evolve its spin, it turns out to be 0.04, okay? And that is why the constraint on the spin parameters here. The more conservative constraint comes from the equation of states, and that is at the level of 0.9, okay? But 0.89 that we have here is also the limit of the waveforms that we have, which can model spins to this level. Okay, so it is a combination of both the equation of state requirements as well as the ability of waveforms to probe such high spins. And these are the two spin priors we use for constraining the properties of the neutron stars that we have observed, or the merger of the neutron star that we have observed. And hence, like, we list all the properties for these two particular cases. Okay, so what I want to point out is first, sorry, I went ahead in my slides. Apologies for that. So it's somehow not working on my slides. Oh, okay, it is there. So I said that the chirp mass is the best measure parameter, and it's not correlated with the spin. And that is what we see here, that its constraints are almost the same for both the spin choices. However, if we look at the constraints on the component masses, M1 and M2, then we see that the upper bound on the masses is different. So since this is a more conservative choice, you get a broader constraint on the component masses. And the same goes for the second mass. Equivalently, you can also see, if you look at this mass ratio that is constrained between 0.7 and 1, 1 being for the equal mass system, 0.7, of course, is the asymmetric system. If you consider the priors, which are as small as, or the limit on priors as 0.05, then you constrain it better than when you can constrain. And again, of course, it has to do the same thing because the spins are correlated with the mass ratio. You get poor constraints when you go for the more conservative choice, which is this. But if you stick to this is actually not a very this is also motivated by the observations that we have so far, and also equally realistic, in my opinion. There are two more things that I would like to highlight is on this slide, and that is the measurement of the tidal deformability. Okay, so the extent to which the companion's gravitational field deforms the other neutron star is measured in terms of some parameter lambda. We'll see a definition of it. And we use gravitational wave observations to constrain it. And these are the constraints on it. Of course, in your 0.05 spin priors, as well as with more realistic priors. And although tidal deformability is also expected to be correlated with the spins, and that is what the effect that we see here. That it is slightly changing when we go ahead. But it's not the only measure. There are multiple ways in which we try to constrain this deformation of neutron stars, and we will see one by one how it goes. Right. So this is essentially that's what I discussed. The only thing that I want to highlight is the two-dimensional contour that we have in the M1, M2 plane. Represents the measurement of the chirp mass. And the shape of this is decided by, as you can see, the combination of both the masses. And the fact that, like, it is the best measure parameter is reflected in the fact that it's a very narrow line. But the extent you can see for the low spin priors, we have constrained the chirp mass to very, very narrow regions. And the values which are here. Right. This is an additional detail, but it's probably very relevant for the parameter estimation studies. And that is that we identify a combination of the spins and the mass ratio, which aptly represents effectively the spin of the system. Okay. And this is also probably the second best measured parameter that we have in general in binary neutron star or binary black hole system. So this is the combination. It's a simple combination of spins and mass ratios. And a value 0 would mean a non-spinning system, while it can take value of -1 and +1, where the two extreme mean that the spins are anti-aligned to the orbital angular momentum and spins are aligned with the orbital angular momentum. Right. Now, coming back to the question of constraining the tidal deformations. In fact, these are the 90% bounds, the dashed lines that we see here. They are the 90% bounds. The other dashed line is the 50% bounds on the individual tidal deformability. So both neutrons are deforming each other. And then, like, you try to measure independently the two tidal deformability parameters, characterizing the deformation as the binary merges or as the binary approaches to the merger. And what is also plotted is this shaded region, which is essentially has been obtained by solving, let's say, TOV equations for different representative equation of a state. And as we can see in the figure, it has been highlighted that the observations which bound to 90% level, the tidal deformity in this region do not favor less compact objects. Okay, so the equation of states that suggest less compactness, but they favor more compact objects. Okay, and that's seen in both the cases. So yes, so this is again the high spin prior or the more conservative prior, and this is the low spin prior, and the constraints are related. Now, this was the first event. We also have a second binary neutron star merger event identified to the best as BNS merger, although the possibility that, like, it could be a very low mass black hole merger or black hole merger or neutron star black hole merger is also not ruled out. But it's a very good likely, it's very unlikely that it is going to be not a BNS merger. Why we couldn't confirm? Because we didn't have electromagnetic counterpart for this. And why we didn't have, I think the audience here knows better than me, but one of the reasons that one can argue is, like, maybe the line of sight is, it's an off-axis event, and the line of sight is not along our line of sight. So, sorry, our line of sight is not along the EM emissions that we have. But that's the extent I can claim. But otherwise, there are many other factors. it's a very distant event. It's not like 40 megaparsec, but it's 160 megaparsec. And that reduces the SNR for this event from 30 to 10. Okay. And that is a big constraint because we do poor measurements of all the parameters when it comes to a low SNR event, including the tidal deformability parameter. Nevertheless, the masses are again constrained. These are slightly heavier. This is slightly heavier than the first event, and these have significant consequences to the measurement of tidal deformability parameter for the reason that heavier the object, less compact it is, which leads to low value of tidal deformability parameter. And as you'll see that a low value for this tidal deformability parameter is a hurdle in measuring these parameters. We'll see the waveforms, exact waveform, which will reflect this particular aspect. The mass ratio measurements are not very different from the one that we had from GW 170817. The effective spin parameter, as you can see, it is consistent with the low spin priors, even for the conservative case. And as expected, the choke mass measurements do not change a lot. And there are constraints for the tidal deformability parameters, but these are also, as I said, this is it involves heavier neutron stars, and hence constraining the tidal deformability parameter is slightly difficult in this case. Plus, it's a low SNR event. So all combined, we have poor measurement of the macroscopic properties of the neutron stars from here. And you can see the constraints are slightly larger than what we had expected. So it includes more equation of states than what is predicted by the observations of the first. Now, this is sort of a summary of the tidal deformability measurements that we have. So the pink and the green shaded regions are the measurements of the masses using GW 1708. Well, I guess I can't see, but probably it is there somewhere. And so the pink is GW 17017, and the green one is for the second BNS event. And as you can see, the masses are constrained to higher values. And the vertical arrow that you see essentially is the bound that we got on the tidal deformability parameter, which was denoted by this. Oh my God, sorry. This lambda tilde parameter. Okay, the second row actually. I think it's slightly weaker, but yeah, this is the row on which the measurements are about 800. The plot is for the low spin priors only, so we have to look at the low spin prior values here. Right. So, so this is the constraint, the upper bound on the lambda values, lambda tilde values from the GW 170817 event. Here, the author has not plotted, maybe just to avoid any overselling of the constraints from the BNS, gravitational wave BNS events. Now, this is, of course, the upper limit, like these two neutron star systems, they are sort of upper limit, observed upper limit for the neutron stars. While there are equation of states which do suggest, so all these gray lines are representative constraints on the masses from different equation of state. And I think there is nothing much relevant, but this green curve that we see here is essentially the double neutron star population in the galaxy. And this is the orange curve is a bimodal distribution that also includes the neutron stars in X-ray binaries or with the white dwarf. But nevertheless, the estimates seem to be consistent with both the models. There is these dashed lines also, which sort of tell how lambda changes as a function of total mass. And this is sort of indicating that it is more close to m⁻⁻⁶ than m⁻⁵, a very small observations here. Now, these tidal deformability measurements also can be translated into constraining the radii of the neutron stars that are involved. Now, in this plot, there is an assumption which has been made that both the neutron stars are sort of identical in a sense, like, both of them follow the same equation of state and have the same properties. And then, two independent methods were employed to constrain the radius of neutron stars. And this is a paper which focused on the measurement of the radius and the equation of state. And I wouldn't go into the details, but this part is more agnostic to the equation of state, whereas this one takes into account in a finer way the information that is going to come from the equation of state, in a sense that, like, it parameterizes the pressure density relation itself. And while both constraints are similar, it seems that the second one is slightly more constraining than the first case. And what we have on blue is, I believe, it's the lowest spin priors, and the orange is for the high spin priors. Okay, so this is the mass radius relation or observations that we have from GW 170817. We don't have a similar study for the other one because it will not probably add a lot to our understanding of this. Now, coming back to so this is what was done so far. And while the constraints are not super tight, they start to come closer to the constraint that we have from, let's say X-ray observations. Okay, so maybe, like, after a few more events, you can combine this information and get better constraint, but it is coming closer to that. And in that light, it is probably important to look at the timeline of the GW detectors that has been proposed. Of course, this is subject to many other things. For example, COVID delayed the operations for significantly, or cut down short the runs. But nevertheless, this is our optimistic timeline for these observations. So we just finished what we call the third observing run, or O3, and now we move to the next observing run, O4, which was supposed to start around March this year, but it's been delayed for a couple of months. Likely it will start in May for sure. And as we can see, it's like, so what we see here is the sort of horizon for these detectors, assuming the sources are binary neutron star mergers. So this is sort of the distances up to which you will be able to observe the neutron star mergers with some threshold SNR. And as we can see that this range is the lower reach, or the lower horizon, is going to change by a factor of 1.5. Okay, so that means if you detected 2 events, you are going to detect 3 events in the O4 PSD. Okay, and subsequently, I think late in 27, you will have O5. So this is called A+. This is called advanced LIGO, and this is called Voyager. Okay, and this again is going to change 2.5 times. That means 2 versus 5 detections in O5 and 3 detections in O4. That's typically what this means. Exactly. And similarly, the other detectors ranges also, but it's likely only Kagra will be able to operate. Virgo will be able to operate at O4 level sensitivities only in Voyager. But nevertheless, we have two detectors, and we have seen, at least in the case of binary neutron star merger, that even if the detector is not sensitive enough to detect the signal with confidence, it can be used to, let's say, localize the source better. And that's exactly what happened. The GW170817 was not detected in Virgo, but it helps us localize the sources because the directions can be combined into the other information and constrain the source in the sky better. So with this, what we expect is that the mass radius relation will be constrained further. Our simulated or some sort of target region, the value or the equation of a state is sort of the pink line. And then it's been shown that how subsequent science runs will try to approach it as we go along. And the cyan is the current sort of constraint. It's like, again, one is making some approximations that the equation of a state is same for both and so on. And again, this is low spin prior estimate, but these are the constraints that we have. And if we go to the projected O4, that is this green shaded region, and finally the O4 will constrain better. So what we see here is with upgrades in the detectors, you are expected to constrain this mass radius relation more and more. And I think this is quite a lot of improvement. Anyways, if you detect something in this range, it's narrow. Now, what makes neutron stars very special is just the duration for which we can detect them. Okay, what we have here is first five events. In fact, this has been converted into gravitational wave event now. First 5 events, these are the expected waveforms. And the longest one was less than 2 seconds long. So we saw this longest BBH merger, which was about 21 solar masses, less than 2 seconds in our detectors. But the neutron stars are light systems. So they enter the detector at the same time, but they merge at much later frequency, a much larger frequency. And as you can see that the waveform of the neutron star merger compared to the other waveforms, and it just goes on for a minute or two. We did have 100 seconds of data. I think here we have about 50 seconds. But it just tells that, if waveform is going to be your tool, these are the sort of events that you should be after, because you can constrain so many parameters with such long waveform. And we are talking about long because other waveforms, even the lightest BBH merger that we had observed until these 5 events was about 2 seconds, while this is about 100 seconds. So you have 50 times more length of the signal that you can. This gets boring with the thing, but it just shows and it's real time. Okay, so it's not slowed, it's real time. So I think about 55 seconds, and now we have merger. Okay, so the last 55 seconds were recorded and plotted here. And this is also very crucial for BNS mergers in a sense that the tidal effects only become apparent after, let's say, 600 hertz or something like that. And if you have a light BNS merger, you get to see a lot of cycles when the tidal deformations are taking place. So this is also relevant for the discussions that we are having here. Now, going into the details of the measurement of these parameters. Okay, I did not explain a lot how these measurements are done and so on, and I will not be able to do this in this talk. But I would just try to sketch the kind of quantity that we are trying to measure here. So this is a typical frequency domain phase of the gravitational wave signal, and it is this information that is most crucial when it comes to the data analysis of gravitational wave signal. And that's why when the waveforms were constructed in the era prior to the numerical simulations and so on, they kept this phase information as accurate as possible, because a loss in the phase information can lead to the loss in detection. Okay, even if you for a BNS event, even if you are unable to model the phase with an accuracy less than one cycle. So for example, if you model the phase, but if you are missing the phase by one cycle, it can lead to non-detection. And that's why this phase was computed to very high order of accuracy using post-Newtonian formulation. What we see here is the powers of V. Okay, it's actually a series expansion in V. V is sort of expansion parameter, and the powers of V denote the post-Newtonian orders that we have. So for example, the terminology is 1 PN correspond to a correction of V square, 2 PN will correspond to a correction of V power 4, 3 PN will correspond to V power 6, and there are half PN terms also. So for example, V cube will mean 1.5, V5 will mean 2.5, and so on. So that's the terminology, but these results are expressed as series expansions in this expansion parameter. It's a dimensionless parameter, and essentially it's a function of frequency. The larger the value, larger the frequency at which the binary is orbiting. And so here, since we are interested in the tidal effects, I have split the waveforms into two pieces. One is what is computed. So the phase is computed using some energy balance equation, where you say that the amount that is lost, the amount of energy that is lost in gravitational waves, essentially is amount by which the energy of the system is reducing. And using that argument, you can compute the phase of the signal. And this is the part which assumes that the neutron stars are point particles. Okay, the same waveform is for black holes, naturally, because black holes can be taken point particles as long as we want. The tidal effect is the one that comes into picture when you go beyond this point particle approximation and assume that, like, they are not point particles but extended objects. However, as I tried to indicate that, like, it's only much later in the evolution that the tidal effects become relevant. And the reason is that when the neutrons are far away, you can, of course, approximate that in point particles, but when they are closer, almost the sizes of neutron stars, at that level, you cannot consider them point particles, and you need, but at that level, already the frequencies are very high. So you can see that the contributions that come are of the order of V power 10. Now, typically, the neutron stars, let's say, reach of the frequency of 0.1 or order of 0.1, and that means 10 power minus 10. So you can see it's a very small effect, and this was the reason why this lambda tilde parameter has to be very large. So for the second BNS event, which included or involved neutron stars with heavier masses, the value of this parameter is lower, and hence it is harder to measure in a parameter estimation problem. Nevertheless, just to give you a sense of how much it is, essentially, if you can calculate, let's say, how much dephasing will occur if you consider the tidal effect. So this calculation assumes a very simplistic scenario where you have two neutron stars, and you compute the phase up to the point that the two neutron stars are in contact. And it assumes some typical values for the love numbers K2 and the compactness C. Let's say, I think, what's a typical love number value K2 for 0.01 or something, or I don't know, I don't remember, but compactness may be 0.15. And if you just combine those values, you get about 14 radians, which is nearly 3 cycles. And 3 cycles, as I said, like even 1 cycle is crucial. 3 cycle is something that you can definitely detect and measure, and that's what we have been after. If you plot them, this is not the same waveform that I showed. It's slightly more involved, although the information in the tidal terms is not very advanced in the other waveform, but it's a complete waveform. This is an in-spiral waveform. And for BNS mergers, it is good enough to work with in-spiral waveform. In fact, the GW170817 event was analyzed using an in-spiral waveform, including the tidal effects. And when we repeated the analysis with more sophisticated waveforms like the ones here, the results were not very different. Okay, it's at the level of 90%. They all agreed. And so this is some sort of depiction of how the waveforms change when you have neutron stars with larger and larger deformation possibilities. Okay, so for example, larger value of lambda will indicate that the neutron star can be deformed more. And as we argued that, like, larger value of lambda also helps constraining it better, because the fact that, like, this is a very high frequency term. And the top is essentially the time domain waveform. The bottom is actually the frequency domain waveform, the same thing. And it just shows the kind of dephasing that you will see. And it becomes more than 2 or 3 cycles when you go all the way till the merger. In fact, this waveform was truncated at the time when the amplitude sort of peaks. So it doesn't include the merger part, but at least goes all the way till you can, as far as the in-spiral is concerned. Now, this particular lambda tilde parameter is a special comp. So we looked at the measurement of lambda 1 and lambda 2, where we independently varied or sampled lambda 1 and lambda 2 for the two neutron stars. But we can also try to measure the combination that is lambda tilde, and this is the combination that appears in the waveform. So you can suitably model a combination of lambda 1 and lambda 2, and then try to constrain this instead of constraining 2 parameters. Okay, it's always good to constrain 1 effective parameter as compared to 2 parameters in a parameter estimation problem. And this is what our results are. So as you can see that this magenta is the in-spiral waveform, which was used for the first analysis, and then it was repeated with other variants of the waveforms, and the results are more or less consistent. There are changes in the bounds, but the bounds are not bounds do not change much. And this shows the level at which we can constrain this lambda tilde parameter, and this is what this is the only parameter that one aims to constrain, let's say, using or one tried to constrain using the gravitational wave observations we have so far, because this is the leading effect. If you can't constrain it well, you can't constrain the remaining that come at higher order. And this, of course, naturally is because of the tidal effect corresponds to the quadrupole. The next order terms will involve octupole and current quadrupole and so on. And this is, in fact, it is completed. In fact, the post-Newtonian theory, in fact, Guillaume is here on us. So this writes the full tidal phasing up to 2.5 PN order, and it sort of parameterizes the tidal corrections in slightly different parameters, the mu plus and sigma plus. but mu plus 2 is essentially can be related to the lambda 2 that we had, or the quadrupole tidal deformability parameter, where the sigma 2 corresponds to the current deformability parameter, quadrupole deformability parameter. And then you have also the octopolar corrections, okay? In fact, the quadrupole contributions also have some sort of asymmetric combination. In fact, you can combine plus and minus to write in terms of symmetric and antisymmetric part. And asymmetric part always appears with this delta. Delta is essentially a ratio between the difference of the mass component masses divided by the total mass. Okay, so it's a difference mass ratio parameter. It is 0 for equal mass and non-zero for the unequal mass case. But you can see that if you have nearly equal mass neutron star, all these contributions that appear with this delta can be assumed to be very small or 0. In fact, for equal mass, it is exactly 0. Nature doesn't produce exactly same mass stars, but you can say that, like, okay, given that there is not much variation in the neutron star masses, for black holes, it may be relevant, but for neutron stars, they are always very small contribution. And hence you can try to characterize the tidal deformability in terms of the quadrupole tidal deformability parameter, or current quadrupole parameter, or sort of octopole variant of it. And we tried to do that. We tried to actually project this earlier formula or earlier parameterization in the language of the parameters that was measured. That means this lambda 2 and so on. So until now, so the BNS, so just to indicate that the current constraint on the equation of state involving all the models, apart from a few, do involve only the 1PN formula. That is, it involves corrections only up to V square. Okay, this paper is only in. Oh, I'm sorry. I have to get used to. This is in 220. So of course, all the results were obtained before that, and but now we have we can go beyond the 1PN term and include the 1.5 PN, 2 PN, 2.5 PN, and this is essentially the reparameterization of the previous result that we saw. And we try to measure all this, okay? But unfortunately, it seems that, so as we argued that this is a V power 10 correction, already very small, and you need large value of lambda parameters to measure or constrain this better. Think about going beyond V power 10 to 12, 13, 14, 15. So it becomes harder and harder to measure parameters which appear at higher post-Newtonian orders. And hence, we'll have to be more realistic. We'll have to essentially try to use all the information that is there in the waveform, but then not try to measure all parameters that are there, because then there are correlations and the measurement becomes poor. And that is, keeping that in mind, we try to have a parameterage which is much simpler than the full parameterization, where we essentially say that we can assume that the contribution from the small the contributions from slight asymmetry in the BNS system, they will be very small, so I can set them all to 0, and hence I get rid of all these parameters in some sense. And I also do not intend to measure in the first go the octopolar term or the current quadrupolar term related to the tidal effects, and hence my parameterization becomes this. So essentially what I have done, I have extended the 1PN relations that we had to 2.5 PN, but characterized only in terms of the quadrupole tidal deformability parameter. So I'm still measuring the same parameter, but I am using a more accurate formula. And what we see is like, if the waveforms are not accurate, it can lead to systematic errors, not just in the measurement of the parameter that we are interested in, but other important parameters like masses and spins. Okay, so it is important to use the full information in the waveform, and this is one step in that direction where we complete the formula, assuming that like in the only formula relevant, so only the term that is relevant for us is the quadrupolar term, and we use a full formula. And this is sort of, the table gives, it's an approximate number, but the improvements can be taken as real. Okay, so these are for the first BNS event, GW170817, SNR of 35. Okay, in both cases. So the phasing, if we change phasing, the SNR doesn't change, because like the phasing cancels out from the absolute, and hence the SNR is same for the events. And what we have on the top is essentially the measurement on the relative error on this lambda2 parameter. Okay, so in some sense you can say the error on the lambda2 parameter is about 31%. When we used 1PN formula, only the terms, sorry, oh my God. Right, only if you constrain this waveform to this formula, then you get a number, and then you use the full formula and get another number. And you can see the numbers are changing from 31% to 26%. A small change, but this is for advanced LIGO detectors. You may have future versions where this change can be larger. And what I have included here is some sort of systematic error, in a sense that if you had not included these additional terms, what is the systematic errors on the measurement of the lambda parameter? And here also it reduces once you use the full waveform. Then you, oh, this is a project. I mean, to find. Right, yeah, so this also reduces. And in the last, I just show some sort of a number to indicate the accuracy of the analysis. Okay, so this analysis is done using Fisher information matrix approach, and we have to invert the Fisher matrix in order to get the errors. And this is the way to, one way to check how good the inversion is. Ideally, it should be 0, but in real life, it is never 0. And the smaller it is, better it is. I think the acceptable number is depends on the person. Okay, so for me, it's fine. But a person who needs more accuracy may even go further down this. So this is sort of. I'm sorry for this. I'm still finding my way. Right. So, and this is the second event. So the last 2 rows are for the GW1905-0425, and we see that here also the errors reduce. So essentially, by using more accurate formula, I'm able to constrain the parameter better. This is an exercise where I essentially use different detectors. So I use advanced LIGO and O4, that is A+, Voyager, that is O5, and also a 3rd generation detector, Cosmic Explorer. And as we can see here is the SNRs go up as we go further and further higher in the detector configurations. This is your advanced LIGO number, this is A+, this is Voyager, and this is CE. The SNRs, typical SNRs are of the order of 30 for A LIGO and are of the order of 1,000 for, and this all is going to contribute to the measurement that we see here. So as a function of lambda parameter, as you can see, it's monotonically decreasing values. And the same thing is also plotted against the masses. There is a gap at 1.4 solar mass because in our parameter estimation exercise, we consider the difference mass parameter, which is 0. and you are supposed to take derivatives with respect to it and so on. So it leads to you are not able to do this analysis for this event. So 1.4, 1.4. So one thing I will mention that the configurations involve one neutron star with 1.4 solar masses, and the other neutron stars can have masses between 1 and 2. And we are using this work, the data from this work, which actually gives us not just the quadrupolar tidal deformability parameters, but also gives us octopolar and the current quadrupolar parameter. So we are going to use this to understand. The second parameterization, and I'll just wind up very quickly, is slightly more complicated. We now remove all the delta terms, but we keep the octopolar and the sigma terms. And finally, the third parameterization is the full thing. And what I want to show is how it changes, how the measurements change as we change these parameterizations. So the first two parameterization, where we neglected in both cases the asymmetric pieces, and this is for advanced LIGO. So this may change for future detectors, but for advanced LIGO, going from one parameterization to the other, where both octopolar and current quadrupolar components were included, doesn't change much. However, if we use the full parameterization, that the asymmetric pieces, then we start to see that the errors become actually larger. And this is, while I have not thought so much about it, but this is, I can understand that the mass ratio is correlated with other parameters, and that is what leading us to the poor measurements. But if you stick to away from the exactly equal mass case, for which anyway we cannot handle anything, we do get more or less similar estimate, but of course there are some changes. And this is an important message. Maybe we should include all these parameters in our analyses so that we get more realistic bounds than we have now. So with this, I'll end with two short notes. Essentially, I have said it already in the talk. So one is that the two BNSS events, or at least let's say one BNS event, has provided constraints which are not extremely tight, but they are slowly, with certain assumptions, they seem to be agreeing with the current observations. And although the second event could not contribute much to this knowledge for obvious reasons, of course, the constraints are still consistent with the previous thing, so that's a good check. And finally, that we have now more additional parameters, additional effects that have been modeled, and all the future analyses should be done with these modified waveforms, and hopefully they will give us better constraints on the equation of the state parameter. I will leave you not with the summary slide, but with I showed a snapshot of a simulation. I'll just run that simulation. On the left, you have matter density evolution. On the right, you have gravitational waves. But we can, I'll be happy to take any questions at this stage.
Okay, thank you, Chandra, for a very nice talk. So questions, please raise your hands. Yeah, Gopu? Yeah, actually, any questions? Okay, maybe someone who's not asked questions would like to go first. Any questions? Yeah, Jacob.
So the tidal deformity constraints which you give, the number which you give, so how sensitive are they to the equation of state itself? Like, are the error bars very much different if I use a different equation of state?
Right. So, for example, this the pink line that you see is, let's say, one very good choice of equation of a state, and the bound that we have is the gravitational wave bound. Okay, so the Cian bound that we have. So yes, it is consistent with the equation of a state that is most possible, but it's not very constraining at the moment.
Okay, and how do we select that the pink I mean, the equation of state for this being.
Well, I think it's just it's one most favored choice. I think nothing else. There are, in fact, this is a very special plot, but these are the constraints, for example, from all different values of equation of the state. So it can be anywhere in this. And here also you can see that it is right in the meat of this gray thing. So far, so good.
Okay, any other questions? Okay, yes. Ashok?
So, I have a quick question, that slide timeline.
With this one?
Yeah, so I'm a little bit confused about Kagra, means how can it sees the very close, means you have purple and gray, so I think some reason, not the O5.
Oh, this one.
Yeah, so it seems purple is very high, then mid, then how is possible for the detector? It is seeing the close region, then middle distance.
Sensitivity increases, right? It's noise, they're reducing the noise floor. So sensitivity increases with time, I think, with upgrades.
Yeah.
So why there gray in between?
I think the gray is when it is not probably planned upgrades in between. It is not taking.
But say first it was seeing 1, 2, 3, right? Okay. Then it will see up to 10 kpc, but the mid region also it will see, right?
This is just, I think the gray represents that detector is not taking data at all.
Okay. Oh, okay. Yeah, so it's. Yes, and then it will be again. Okay, that.
Actually, okay, let him go first and then Prabhu.
Okay, can you please go to the slide 5?
Slide 5, okay. Yes.
Okay, so you maybe please correct me. You mentioned that this bound actually favors more compact stars, right?
Right.
So how it can be concluded actually? If you can
No, so more compact means smaller lambda values, and our 90% bounds are these. So starting from
so
let's say,
compact in terms of I mean, which parameter you are concluding that?
so harder to deform sort of thing. So if you want to talk in terms of lambda, so larger lambda value, easier to deform, less compact, and smaller lambda value, harder to deform. So in that language, from larger lambda value to smaller lambda value leads to more compact from less compact. And since the 90% bounds are below this, we say that the observations favor equation of states which give out more compact neutron star than the less compact ones.
Okay, so do you have any guess like what is the pressure or whatever for those kind of stars?
No, I mean, nobody knows, but I mean, we can always try to solve TOE equation for different choices. For example, here this was exactly done. So here we did not, here we used a relation which was sort of use common equation of a state, but here we actually parameterized the pressure to density relation to find and solve it exactly to get the radius constraints. So yeah, I mean, you can try out. We don't know what is the right equation of a state, but yeah, there are.
So actually,
Maybe let others ask, and you can ask in the discussion. So Gopu, I think, and then you can ask in the break, I think. So request to keep your questions short and succinct, and we can discuss more during.
Very nice talk, Chandra.
Right.
I have a couple of questions, but I will be very quick.
Yeah.
So the fact that you have lambda to tilde is better estimated simply because you are adding post-Newtonian corrections, so somewhat inflating the previous, the quadrupolar or the dominant lambda. Is that the way to understand that?
Yeah, I'm just completing the waveform.
Yeah, sure.
Yeah, and
Perfect.
I'm expecting that it will get better, and it does get better.
Yes.
Yeah.
So with the post-Newtonian corrections to the, as you correctly pointed out, reparameterizing this.
Right.
So how crucial this will, if you have an independent estimates or different estimate for the mass ratio, better, will that be interesting implication for all these in the sense of, getting the radius things constrained?
Yeah, I mean, we do measure all this together, right? So
Sure.
if there is a system which is favoring better estimates of mass ratio, it will reflect in the tidal deformability measurement also.
Okay.
Yeah.
The last question, just is for, so since these are 5PN contributions, you are not incorporating 4PN and the higher order point particles. So there will be a systematic bias.
Right.
Is that, I know, of course, you can put parameters and maybe do it in EOB too, but they have been taken care, or they have been sort of quantified so that it will not flow into your estimates.
Yeah. Well, there is always this element, right? I mean, you don't have, we don't even have 4PN non-spinning piece. So
we can put it from the test particle.
Yeah, but I would like to see it as an independent effect, which you start to see only 600 hertz beyond. So if you have, so for example, we argued that the number of cycles in tidal deformability are about 2.5 or 3. If I can capture the element of these 3 cycles, we'll be happy. Okay, and it will put a constraint on this. Yes, there are 3,000 more cycles and they needs to be more accurate, but to me, this is a different effect that is appearing beyond 600 hertz, and you should be able to constrain. Despite, yes, there are always systematics, and in fact, when we look at the constraints from, sorry, I didn't. So for example, the constraints are not exactly the same as in spiral waveforms when you include the EUB waveforms and so on. So they will be slightly different. And yes, the 4PN piece should all. So yeah. So I mean, I'm hoping that it will be consistent even then. Yeah. Maybe Guillaume can answer it better, but this is the extent to which I would like to think. Yeah.
Yeah, thanks, Chandra. Slide 9, when you look at these sensitivity levels with these different observation plans.
Yeah.
So what percentage of these planned observations are usable? Do you get affected by interference, and do you have to worry about them? Is it growing in time over years? What kind of?
This is always a concern. It's like a routine thing for us. So every data set is very dirty to look at. In fact, you would not believe if you see the first event data set. All of us know. So while we were detecting this, just before the merger, there was a glitch. And it just offsets the detector in some sense. Yeah, so you have to remove these artificial elements and then have a cleaner data to look at. But Gopu, you wanted to make a remark.
Imagine a scenario where that glitch was closer. I mean, training the.
No, I don't think. Well, yeah, probably, yes. I mean, always, but it's not that so we tried to model that part using, let's say, burst algorithms and replace the data. So, I mean, it's not like, we are losing 100% information there. But yes, I mean, given that we have essentially 3 cycles maximum, there can be an element which could have been better. Right. And this is the Livingston, which is the most sensitive detector actually.
So this is about the slide 9.
Yeah.
So I just want to know, what is the waveform model that is implemented to get those distances or some? So since there are various waveform models.
Yeah. So this is as I said, that this is assuming binary neutron star as sources. And you can use the simple in-spiral models that the ones that I showed to get this range.
I think 1.4 solar mass, I think, right?
Yeah, these are all BNS, like 1.4, 1.4. Yeah, exactly. So you can use this waveform to
Okay, but
calculate.
is it depends upon the very waveform models, like which waveform model you are implementing, or?
So this is just indicative. So we don't do, I mean, if you want to compute the horizon distance for a set of events, then you can use more sophisticated waveform where you also include the information for the mergering down. But to just indicate that how what is the typical range up to which these detectors will be sensitive, we can use the Taylor-Active waveforms, which are in spiral waveforms.
Okay, any questions from Zoom participants? Just quickly check. Okay, so let's thank Chandra again for a very nice talk. So we've all actually eaten up 10 minutes of the break. So maybe we meet at 12:05 is okay. Okay, so thank you all. And further questions you can ask Chandra during the break. Okay. Thank you. So for the online participant, Ramesh, I think we'll be meeting at 12:05. We are just having a break now.
Okay, sure. Thanks.
hello, mic check. Okay. Well.
காலையிலே போட்டோன்னா 90% இருந்தது. கடைக்கு இது பண்றதுக்குள்ள எல்லா இதுவும் நல்லா இருக்கு. இது கூட அது தெரியும். இந்த மாதிரி ஃபுல் டே ஃபுல் டேல கேப் கேப் சாப்பாடு
fixed, carbon adsorption and storage, and
Just to speak. Can you hear Ramesh? He should be able to. Can you hear Ramesh? Hello.
Yes, I can hear you. Sorry.
Okay, thank. And you are able to see the presentation slide, I think, right? Which we think it is visible here.
Sure.
Yeah. Okay. Good.
Yeah, so okay, I'll start. Hey, welcome back, everyone. We'll discuss about pulsar timing in SK era and what is the future of IPTA. So we have two experts on pulsar timing and radio telescope instrumentation. We have Mora and Prabhu, so they will lead the discussion today. So as you see, Prabhu has here some prototype of SK, so which Prabhu will start by explaining her.
Yeah, I think good morning, good afternoon, everyone. And it's going to be Manjari, myself, and Nora. And I'm sure other experts here, please pitch in. And it's not going to be one person or two people leading this thing. So SK is coming up, and it's going to be deployed in two sites, as you see there in this picture behind me. One is in South Africa. For those who know about SK a lot, kindly excuse. The South Africa telescope on the left is a dish type, and then one in the Western Australia is it's a different kind of a lock periodic antenna. The mammoth size of this telescope is going to give us, and it's the way it is organized and designed, it's going to give a huge sensitivity boost in the radio telescope that exists so far. both the places are very radio quiet, and the Western Australian site is even more. And you can see it from the number of people density that I compare. Apologies, I didn't put Chennai density. It must be much more than that. And you will see this means we are going to get a very good quality science data. Okay. As you know, RFI cleaning and things like that will be required when we actually start processing, especially in the MW experience, I can say, you can straight away start using. There are only very few channels get affected, and except the satellite ones sometimes. Okay, now just to give a feel for the complexity is going to be a little different than science data processing. And I think we have to, right now, the SK is in the bridge, building phase. The telescope is still not ready to be operational. So this is also a time that we can actually look into a lot of commissioning related and instrument characterization related. It's like 30 years ago how GMRT was. So people who were able to get into GMRT at that time are the pioneers today. So we have a very good opportunity to get into SKA from this phase onwards, where we understand all the instrumental backgrounds. For example, if you have to use one of the big telescope, VLA or others, we get only data. People don't even know what actually makes the telescope working. So here there is an opportunity. The complexities are a little different. The antenna here in the left is a dish. We are familiar with it. And still there is going to be complexity here. Meerkat is going to be smaller dish, 13 meter. 64 of them will add to the SK telescope, which is the remaining 120 odd telescope, which will be 15-meter dish. So polarization and aspects related to using the two different dishes are going to be an issue in terms of some very fine studies, which we want us to look at. On the right-hand side are the log periodic antennas, where if you can, sorry, I think, yeah. Sorry, the slide is not moving, yeah. Yeah, if you see, the antennas are very different from what we are used to in the GMRT experience. They are going to be log periodic antennas. The left-hand picture shows how the individual dish equivalent a tile a station will be, which consists of 256 antennas of the one which shown in the right-hand side. Each antenna is this high, and it covers a wide frequency range, 50 to 350 megahertz. Supposed to see uniform sky coverage, but it does have some aspects related to different angles. And these are the things that needs to be worried about when you want to do fine study using this instrumentation. And more complex thing will be polarimetry with this antenna, because the antenna doesn't turn towards the direction of the source. So as the source passes by, the X and Y polarizations are going to have this change of pickup, and that we need to do this inverse Jones matrix correction. These are the aspects less explored, but they will become very crucial when you want to do high fidelity experiment with these telescopes. Currently, the entire community is working to get this instrument going. It's a mammoth challenge because 128,000 of these right-hand side looking antennas will have to be deployed in 512 such groups seen in the left-hand side. So the current progress as of now, the left-hand side groups have been tested, and a few of the commissioning experiments are going on, but a lot needs to be done as far as to understand the electromagnetic abilities of these antennas. So I'm going to just go into quickly to, yeah. Phase one, which is 5 to 6 years from now, all should be in ground. At least 80% depends on the funding situations. So this is only to lead the discussion. Okay, so there are more slides. We can go into. There are a lot of areas Indian teams are contributing, and it's an international project. As a big science book is written, and I am not. Sorry, I'm going to put this in a different form so that we can jump to different slides when required. So one is expecting SKA. Many things are going to be tried in SKA for the first time in a real time. Okay, timing, it will produce a folded profiles at the end of the observation. For search, it will give candidates at the end of the observation, which has never been done in such large telescopes in big installations so far. So it's a mammoth challenge, and variety of areas where contributions are still required. And as you will see, the chart on the right shows how discovery space has been occupied by the big telescopes. So the larger the instrumentation, so more sophisticated, more discoveries have come. Parks, multi-beam. So in SKA, we'll have 1,500 beams looking into the sky. Okay, at the same time, with a low frequency telescope, there'll be 1,500 directions search and 16 timing beams will be there. So the idea is to discover more and more binary pulsars. That's a red color computing problem that's shown in the right-hand side, the acceleration trials. So that's one of the primary focus to find for looking for binary objects. So there's quite a lot of work going on from India and also from people across the world. And there is more to be done still. And this is the nice time to map our problems from existing telescopes to SKA-like scales. And yeah,
So I think there are a few highly accented pulsars have been discovered with that acceleration jerk search.
Yes. No, but not short orbital period. So
Those will not be, I think, difficult even if you don't include jerk.
Okay.
So Prabhu, Prabhu, I was thinking means what you just ended, that our experience with present telescopes. So one thing means those will be radio quiet, that is good for us, but what to do with satellites? Satellites will go there anyway. Military
That's not a
will
point.
shoot you down.
Yeah, satellite is a big problem. And as you will see, we have already with GMRT, people with experience on GMRT have found it's very hard to plan an observing session.
Yes.
And with all this OneWeb, Google, and other people, the space agencies in SpaceX and other agencies are coming up with hundreds of satellites and unrevealed pictures, publicly available, not publicly available pictures show hardly few degrees space between a satellite track. And the effect of it is not clear what we are going to.
But those are, will they be a problem? Because some of them may not have the, when you're looking for up to 350 megaparsec, and even if you megahertz, your beam may not interfere. They may be there, but they may not emit in those frequencies. So you are not to be worried that much.
Yeah, experiments done with the MWA actually show they are not really reflecting, they are not transmitting.
Yes.
But they have huge reflecting surfaces, and that reflects yet RFI back to the telescope.
Yeah, so it will be an RFI problem rather than, right? I mean,
yeah, it's both, right? I mean, RFI induced due to whether they are coming on the way.
Do you have any slides on RFI mitigation?
Yeah, you can talk.
I mean, because I'm probably just going to say what you were going to say, which is just that, like, the nice thing about an array is it's much better for discriminating RFI than like a single dish telescope, because you can have multiple, adjacent beams, and the RFI will show up in all of them, and a real signal won't, so you can do this like active RFI mitigation, where you actively get rid of stuff that shows up in multiple beams, keep stuff that's independent to one beam that's localized. So I guess I'm worried about the RFI, but I think that by the time the SK is built, that these active RFI mitigation techniques will be really well advanced and computationally feasible. And so it's not going to be like a showstopper,
So that will be mission.
I don't think you need machine learning. You can just have like frequency time grids. And if the same signal shows up, if in the same frequency channel is noisy in multiple adjacent beams, then it's RFI and not a real signal, stuff like that. So not necessarily machine learning.
Yeah, what in pulsar observation, what has been planned is to have multiple beams, nearby beams are correlated for RFI signatures. And that's something that helps. The problem is not just avoiding it, but the duty cycle of observing time that gets affected when we drop the RFI affected signals. So both, which means our sensitivity will come down. There are low-level RFIs, and that comes from all of our mobile phones and internet connections that we have exposed wires everywhere. Things like that appear at low level, and that will put up a limit on the sensitivity of the telescope. They are buried, and high integrations will show up when you start folding for a long time, and then the baseline will be set by these RFI levels. So it's actually possible to remove, like Mara pointed out, with some caveat on time duty cycle of the good data.
Okay, so I've confident with searching this 20,000 pulsar, but it may not interfere with the time.
I mean, I'd say for the searching, yeah, it's a big problem, but there's where machine learning comes in, you know, where you have code that can discriminate pulsar signals from other signals. Hopefully I mean, right now, even machine learning codes can do it with 98 or 99% efficiency. They can discriminate pulsars from RFI. For timing, I think we're a little more immune to RFI. You know, for like PTA timing, we're averaging over hundreds of thousands of pulses, you know. So most of it gets kind of averaged out, you know, unless it's very, you probably want to zap, like there's some frequency channels you're just always going to be zapping, right? Because they're going to be very noisy. But for timing, I think you're a little more immune to it.
Yeah, for timing, beams are even more, it's voltage beams, and they are slightly more narrower than we get the full baseline benefit of the telescope spread, and they are less susceptible. Yeah, there are challenges we can't completely say we can ignore, because the number of electronic gadget usage is increasing with these electric cars, and so on. Everything we are moving into electric. So keeping the place, LED lights, they throw a lot of kilohertz. So lower frequency observations gets really contaminated by the red noise.
Yeah, but can have Faraday cage kind of thing too. The Uti never used to have two lights, right? I remember that.
Yeah.
Now they have.
Inside, yeah, Maura has.
But no, I'm just asking, is the plan to have all the like heavy duty processing happen? I mean, I know there'll be digitization at each dish, right? That's what you said the other day, like the signal will be digitized at each dish, but then like the heavy duty computation, like the pulsar searching, for instance, is the plan that's going to be happen like well off site, right? Or is that going to happen locally?
In the case of pulsars, originally it was planned to be done in the site.
Yeah.
And now, because everything is digitized for the mid telescope and also for the low telescope, and also a large bandwidth is now available. One is contemplating to bring the data processing to outside the site.
Yeah, that's better RFI wise, at least.
Yeah, more than RFI can be handled by this Faraday cage, put the instrument inside the Faraday cage. The more than that, the power in the site is limited, how much electric power is available. So we're not limited for what algorithms to run and how complex the computing machines are. So, okay, sorry. No.
What's the question? No.
Prabhu, what about the data storage and other plans? Like
Sorry, data storage.
Data storage and data transfer also. I mean, how are that going to be managed in such?
In the case of SKA, switch. So I hope I'm able to zoom it a little bit better. So what one see on the top of this, the SK, both telescopes we'll have two pipelines, two major pipelines. One is for the time domain astronomy, which is called non-imaging. Obviously, the name probably given by the imaging people. They said it's not imaging, it's non-imaging. So the bottom pipeline is for the time domain, and the top one is for imaging. So these things happen in the site, and then the data goes to a global distribution. So there'll be science data centers throughout the world, at least some major parts, so that the regions can accept. So there's a science regional data centers. So the data will be sent across to different places, and the regional centers will have computing capability and being able to run these data, store the data in that region. So that's the kind of a data archive.
So I have already, I always wondered, so the high frequency in South Africa, low frequency in Australia, the data will have to be combined. How are we thinking about that?
Yeah, the data, once they are collected from the two places, the data are for a particular application. If the data needs to be combined for our timing purpose, for example, they reach the regional global centers. Global regional centers
directly from observatory.
There is a fiber connections established.
Okay.
Already exists, and there will also be dedicated connectivity. The connectivity will be enhanced further.
Okay.
And regional centers are still coming up. Only China has one, and few other countries have. And India is still contemplating to have one, and still funding, based on the funding situation, it will come up with. So.
Thank you.
So would it be possible to do simultaneous observations from low and mid?
Yeah, the low and mid, it's basically a few hours, and it's again limited by what is the longitude of these sites. It's about 2.5 plus 2.5, 5 hours away. So we will get only 2 or 3 hours common time on a same target. So which is going to make our life a little harder to plan, but it is possible.
Okay. And coming to the satellite RFI, so I'm just saying it from the NPTA point of view, you know that some of the satellites are like monsters for us. So if we identify them, and this is related to your machine learning algorithm too. So let's say we identify those satellites, for us it's MEOS4, and then concentrate on that, prioritize and then decide the slots based on this priority list in your machine learning algorithm. So would that, maybe that would help?
Yeah, that will help. I think there are some ongoing efforts on thinking on how do we propose observational plan, but most likely there's going to be it's going to be a little difficult to do that in a very systematic manner for a large telescopes, unless those things are pushed from the very early time of the scheduling plans, right? And of course, such observational plans are possible. We can always have them for specific observation, but you have to be another observer also would, another science user also would be wanting to use them around the same slot. So with SKA, what is going to be possible is there are many commercial modes, which means you can, a few of the observation can run simultaneously. We don't have to be necessarily commensal modes are possible. So some observations can run. So one may want to probably plan it to maximally utilize this. And this is also the time to worry about these kind of concepts so that we have a maximal benefit coming out of it. Once somebody freezes this, mostly it will get frozen by managerial reasons sometimes. And or whoever sits on the top of the planning and their science case interests. And there's nobody speaking about it, it'll get done in a different way. So we have to have people watching this.
Hi, Prabhu. I have a question. Recently, I saw a paper where they have discovered a material which can allow certain radio frequencies and block certain radio frequencies or something like that. So can that kind of materials be used in this to effectively, restrict the RFI?
No, can you say that again? Sorry, I
So,
missed that first.
I have read a few some paper which it's about some the discovery of a material. I think which blocks a certain part of the radio and only allow it only certain part of the radio will be allowed through it. So can that type of materials be used to remove RFI or yeah.
No. Yeah, I think they are probably for phase 2 of SK. Some thinking can happen in that direction, but practically it's difficult to have any such small solutions for a largely spread sensors, right? They're kilometers away, the antennas.
So just one comment, I think we're discussing a lot of technical issues, but let's spend some time on the science issues also. Let's assume all these problems will be solved, and then let's have some discussions on what science we can do. But I think Jack,
Manchuri, I think want to take over this.
So, before you start that, Prabhu, I have one question. So in the data reduction aspect, for example, when we are going from filter bank to the PS archive fits, so are there now techniques or are people working on techniques where this is done in a parallel, there is a parallel script running for this aspect also so that we get these data products faster? Or at this stage, I mean, at this stage, are there parallelization which is going on? When we go from filter bank to PSR fits, if we need PSR fits, like for the ones.
Yeah, for the SK science data for the pulsar goes into fits. Fine. It gets written out as a fits format and also in a folder. As time goes by, there's going to be there will be dynamic spectrum and also FFT outputs, complex voltage recording format. They'll be available.
Well, no, I just wanted to clarify, like for the searching application, like all the raw data is not going to be stored, right? Ever. I mean, it's just going to go through a real-time search processing, right? And then candidates will be like data on candidates will be stored, right? And for the pulsar timing, I would assume like we also would store some very compressed, like all you'd get would be a compressed data product, like some number of coherently dedispersed frequency channels, right? And profiles stored every, I don't know, second or something like that. It wouldn't be the raw. I don't think you'd ever store the raw data, like the rawest form.
Not the raw data. It'll be the folded in a folded form. It'll be a fits file. And also for pulsar timing, the volume is not going to be huge once you store the fits. So yeah, for search, it will be directions and candidates. And for FRB, it's going to be a different problem. That is another area right now. I think we are finding the parameter space is expanding since SK specifications have been drawn. How many DMs you want to search for? So that number has increased. That means it's going to be either dropped out of SK or it's going to be modifying the SK specification. So if anyone has interest specifically, we have to talk about it also in the right places to make sure that the parameter is not missed.
Obvious, but I think for FRBs, you're just going to need like really good machine learning algorithms because there's so many single pulses, so many things that are going to look possibly like dispersed single pulses. So having like really, really accurate RFI mitigation algorithms is going to, because you have to save quite a bit of data for the FRBs, right? Like you want very good frequency resolution and the whole, you want maybe like a second around each pulse or something, which can be probably the most voluminous of all this if you don't have a lot of good machine learning to get rid of all the not real stuff.
One of the early work that we have done, Balchand Joshi, Arul, and a few other people, all the NPTI collaboration have worked in trying to see how do we map the current pulsar observations, timing observation into the SKA. An effort has been done and it's coming out as a paper so soon. So that has been done based on the sensitivity calculation. Now that means the entire PTA pulsars, if you want to observe, how are we going to do these observations? And that's an effort that's ongoing. Yeah.
Just to add one comment to that, I think it's really hard to do right now because we actually, like right now, we're limited by radiometer noise on almost all of our pulsars. So I think we actually don't know like what the fundamental limit is for timing a pulsar, right? So with the SKA, it might be, if we observe like we're doing now half an hour, that's pointless because we already will have hit the fundamental, jitter limit on all of our pulsars, right? So I think it's really hard because we just actually don't know what that, can we get to like 10 nanoseconds? Are many pulsars we're only going to get to 200 nanoseconds? Like we really don't know.
Yeah, hopefully if we can discover more pulsars, then as a probability, probably we'll get more very good low noise pulsars. So that might help us.
Fast is finding a ton of them.
Yes.
Fast is that they should hit that limit more obviously than current telescopes are.
Yeah, so I
Yeah.
have,
Sorry.
oh, sorry.
No, go ahead.
So one thing about SK, I feel it's both we have in southern hemisphere, so we'll miss good pulsars in northern, right? So why means something maybe not as big as SK. If we had something like SK in say Scandinavia or Alaska or
Yeah. So hopefully that's what DSA supposed to do. This is the synoptic camera deep. This is
Late charge, but yeah, I think there's like there's FAST, which isn't, a telescope like this, but I mean, that's in the Northern Hemisphere. But then in the US, in the US, like there's NGBLA and DSA 2000. And so both of those are going to be arrays like in the Western United States that are now being planned to be SKA precursors, but I could see with time them getting built out to have maybe not comparable sensitivity, but close to comparable sensitivity that could cover Northern Hemisphere sources.
Still maybe southern, right?
Well, I mean, it's at a latitude of, it's in New Mexico. That's probably 25 degrees or, something like that. I'm guessing, I don't know, but it's not like, it's pretty north.
We had something in Alaska or somewhere that might be better.
Well, DSA 2000 it'll have an extremely wide field of view. So it'll see things all the way up to, declinations of 90 degrees. So I think it's good enough. Yeah.
Most of the galaxies are south.
Neither of those are funded yet, though. Like they're both just being planned. So.
But
yeah, for PTA purposes, we're definitely going to want data from a Northern Hemisphere telescope to complement because we really want full sky coverage. So it's going to be really important for the PTA at least.
I know, I'm just, again, yeah. So this is about the FAST, right? They have a problem. They are discovering plenty of millisecond pulsars. I think they have total close around 500 or something, not millisecond pulsars, but the timing is a problem. Therefore, getting their jitter limit is also a problem for them. That's what they were thinking about, the one in Xinjiang, but that's getting, I don't know whether they're going to build it. Anyway, that's off the, so
yeah, it's a huge problem.
Exactly.
It is a huge problem. Just anecdotally, one of my grad students, her name is Victoria, we're following up fast sources with the GBT. And we think of the GBT as a large telescope, right? I mean, it's 100 meters. We can't detect some very bright fast sources, and it goes like the collecting area, right? Like it's not surprising, but it's pretty shocking actually, just having the firsthand experience of, they are sending us candidates and we're looking at these plots with fast, signal to noise of 50. And we don't see that with the GBT. And they, it's a huge problem actually.
That's yeah. So it's slightly technical. I mean, not technical in the sense that as Prabhu wants more students to kind of get involved, it's an excellent idea. So maybe what some of our younger, students who are entering PhD, maybe we should think about, with Prabhu and with your help and all, what are the things we should, get so that they can get trained, so that they can slowly walk into that and get, like the machine learning algorithms, many things which hands-on experience, precisely. So that is something, not just the theory and, black hole gravitation. No, that anyone can do. But
even all kinds of science positions, technical positions connected with the SK, there's a funding has been very attractive funding has been sought, and government is almost just almost nodding. Okay. And if it comes through, there will be postdoc positions and engineering positions and so on. The connect person name there. Okay. And it's a very, very 10-year long plan. It's a good opportunity.
Is our Nirupam or?
Yeah, Nirupam Roy.
Yeah, sure.
Sorry. So
he was sick. You could not be.
There's quite a lot of other and ongoing works also that's listed there. And we still have people needed in the Pulsar area to contribute from India. We are right now contributing at the level of half FTE only to the ongoing. We probably are immediately availability for another half, and possibly go into one. It can be 3 half FTEs.
That will be great. So to encourage you people, so I would like to say, means you all work with Balchandra, means he understands every aspect of pulsar science so well. But he told me the story, means when he first joined NCRA, GMRT was under construction. And he used to go and sit with the engineers and ask questions. So apparently once engineers complained that scientists are disturbing us to build the instrument. Okay, but still they did. So because he did all his hands-on, he learned the things, he understands things so well. So this will be a good opportunity if you can catch Prabhu and do some hands-on experience.
Well, just one concern. What you said is right, but maybe this is not part of this discussion. Right now the pressure is on everyone is to get papers and first author papers and whatever.
Again, so why is this pressure who are putting? It is on us to change the scenario.
This is a issue all over the world.
So when we look for postdocs, probably we should not only look on the publication list. We should look on the enthusiasm and.
Sure. I think you had a question.
Yeah, my question may be slightly off topic. So when this SK for the upcoming, PTA signs with the upcoming SK, what are the plans? Are we including more pulsars and adding in the baseline, or are we observing the same pulsars?
Yeah, so first of all, I do not speak for the SKA because the US is not a member of the SKA consortium. We're being very reluctant, but I think for sure, obviously we want to keep the baseline on our existing pulsars because our sensitivity goes like some power of the timing baseline. But I think for sure we want to expand the array really significantly. Our sensitivity to gravitational waves goes linearly with the number of pulsars. So if we,
But will we get that, some level of sensitivity when we add the pulsar, when it has a very small baseline compared to the baseline we already have of the 60, 70 pulsars?
Take time for the new pulsars to start contributing. But it's worth it. Because we're looking at, the next century of characterizing the gravitational wave universe and beyond, right? Like I don't think we can have that short a lookout, like maybe, and then the sensitivity is so high, I don't know the numbers, but I'm guessing that within even just 3 years, these new pulsars that are added with the SKA are going to be contributing equivalent sensitivity to the pulsars that we've been timing for 30 years, just because of the dependence on the RMS. The other thing I would say is that for continuous, we'll be in the regime, once the SKA is built, we'll have characterized the stochastic background pretty well, most likely. So it's going to be mostly like a single source machine. And for single sources, a 3-year, very, very sensitive data set can be really useful. Doesn't matter, we'll be detecting high frequency, single sources. So I think, yeah, I think we want to, obviously there's a limit, right? We don't want to be timing pulsars with like 100 microsecond RMS.
Yeah.
But I bet, I haven't done the calculations, but I bet there are hundreds, maybe 500 MSPs that we can time with comparable level to what we're doing now with SKA. And we'll like even out the sky distribution, which will be really valuable.
Thank you.
Any other questions, comments? Well, maybe one, like, so what is the holy grail which you hope to or dream to do in terms of science with SK? For pulsars, I mean.
You want to go?
I mean, obviously the gravitational wave stuff, right? Like a catalog of supermassive black hole binaries. We should detect many, many single sources, right? But then there's also all this like, binary pulsar search. There's all these exotic pulsar binaries that we haven't found yet, like a pulsar black hole binary, really setting limits on like the fastest spinning pulsars. It's also going to be really important for LISA, for planning for LISA, like detecting like very compact binaries, because we could detect binaries with only 60 seconds of data that may be in orbits of minutes that we can't do with our current telescopes because they're not big enough. So I think like LISA science, right? Like preparing for LISA science is really important. Yeah, test of GR, like more double pulsars, that'll be cool.
Something which no other telescope can do.
Oh, okay, so I can add to that because maybe 10 years ago, double wide draw binaries were considered to have a period minimum around, I think 60 minutes or something, like I can't remember exact number. So people were a bit, and all the LISA stochastic noise were all computed based on that kind of consideration. Now they have double wide draw. CTF has picked up with 8 minutes or something like that, and they eclipse each other. And these are going to be, if the LISA doesn't see them after a half an hour integration, the mission is a failure. So that's the kind of calibration sources they are. Now, in the case of double neutron star binaries, which are slightly compact than double pulsar, LISA will have to see. And that seeing is actually in terms of gravitational wave emission too. So this will be fantastic probe of, because the LISA H plus and H cross will give you the inclination. So you don't need to worry about, for example, Shapiro, because that information is already provided out from gravitational wave. So the multiple things you can do. Of course, the classical effort will be to measure the quadruple moment of a black hole. If you have a black hole pulsar binary, to go into, we were yesterday kind of briefly discussing, this is coming from the periodic contributions to now I can't get the name of the delay, but Romer delay, periodic contribution induced by the non-Keplerian, anyway, so blah, blah, so.
Any other questions, comments? We still have about 12 minutes. I think according to watch. Anyone who hasn't spoken up? Wait.
It's very simple question. What are the prospects of VLBI with the SKA? I've never heard of that being spoken anyway. So that prospects, right?
Oh, yeah, no, please go ahead. And I.
The question is whether it exists or what is the prospect?
The timing beams are basically VLBI beams, right? So we have 16 beams, so they can be used. We can't, of course, record all the beams, but I think about 5 beams can be. Oh, it's sorry.
Right.
Okay, it's not. Sorry. No, we'll be with other telescopes, for example. Yeah, and it's not.
Yeah, just like a scientific prospect is we should be able to measure pulsar distances and like parallaxes very, very accurately. And that's going to completely transform, gravitational wave astronomy, because we'll be able to use the pulsar term in our single source searches. We'll be able to localize sources much better. We'll be able to track their evolution, like see their evolution between the pulsar and Earth terms, like all this stuff that's just a dream right now, but we should measure parallaxes to enough sources with SKA that it'll be, that'll be really transformative. Well, either through timing or
not using Australian and South African. That's not possible.
well, we can either do it through VLBI or through timing parallax. Either, I mean,
Are there any implications for you know, if you have an independent estimate, because they do differ now. So that will be a fantastic project to kind of do. I don't know whether somebody has done it. Imagine, we have lots of softwares to kind of simulate and see whether what kind of parallax and whether we can trust the timing parallax to the level of.
yeah, I don't know. Right now, some pulsars have better timing parallaxes and some have better VLBI parallaxes. I suspect the same will be true. Yeah.
So any questions from the Zoom participants? Whoever is there. Okay. Any other questions here? Yeah.
So I just have a very general question. So how likely are we able to solve the neutron star equation of state problem with SK? So
Okay. So means, see, for that you need not only it is a few steps, right? First, if you want to use timing to constant equation of state, that probably you know that recent double pulsar result, and Mora is one of the authors. So it was from 2004, it took a long time to give the constant of lens threading effect. So if you first you have to discover more such relativistic, say, double neutron star binary, and there we were means say the pulsar is the first and the companion is slower. So we need something like that. See, if your slow pulsar is beaming to you and fast is away, then you cannot do, because spin orbit coupling is stronger in the first pulsar. So you have to be lucky to get some good double neutron star systems like that. And then if you find, so you do pulsar search, so you find good some sources. Then obviously as SK sensitive, more sensitive, and there are special timing features. So but it will not take 15 years to find the lens threading effect and all the relativistic effect they found recently. So that will help. But again, there are other efforts like from gravitational waves, so they don't depend on SK.
combination of the very precise mass measurements from GW and the moment of inertia from.
Yeah, so that is what I am saying, moment of inertia through lens threading effect. So that has been done only for the double pulsar, right? And that Mora can tell you all the story. So it took more than 15 years, right? So because the science of timing is like that, the more you have data length, your timing accuracy becomes better. So for SK, if you find such type of system, probably it will be faster.
Double pulsars we are expected to detect with SK, and accordingly, there's some.
Yeah, there are, you want to say?
Yeah, I think, I don't know that I know the number specifically for SKA offhand, but it's certainly been done. Like we know 20 DNSs right now. There should be of order, like, hundreds of them, something like that. And then there's a big uncertainty there, right? Because we only know one double pulsar where both pulsars have been beamed towards us. So there's a lot of uncertainties in extrapolating from one. But there should be more than one. Yeah, it's certainly possible to do this calculation, right? Like there's this code called PSR Poppy that will like populate the galaxy with pulsars of some description and put in all the selection effects, and you can do that for the SKA I don't know the number though offhand.
Thanks.
I mean, now we have 24 accreting X-ray millisecond pulsars, and the NICER is doing a fantastic job there. Therefore, it will be curious to know whether, the next generation guys can, by picking up more accreting X-ray millisecond pulsars, can put amazing constraint on the mass radius relation, going in a slightly different way. It's not timing, but it is timing. Yeah, and so their ability to constrain equation of state may be better than even third generation. I don't know. I mean, it is definitely possible because there are lots of the biases, uncertainty, what Chandra was talking about, right? I mean, in the sense of we have not put many in between, Guillaume is working very hard on the 4PN, but the other uncertainties will come in. So I will say mass radius, maybe the X-ray will do better. I think, I don't know.
But even nicer,
but it will.
Any other questions?
So as you would have seen, the earlier instruments, the big instruments, the telescopes that have been very popular, have been built, and only very few people were involved in building them. And today the scenario has changed. A large number of people, contribution from many countries become required for most of the massive scientific projects. And that also gives an ample opportunity that was never existed before for people to be aware of what is coming up. And this telescope is coming up, and it's useful and important. And I think many of us will go away from the scene when the telescope is fully operational. And it will be, when it is fully delivering what it is, like the way GMRT, VLA, or GPT is giving, and it will be only many of you who would be there. So it's a nice time to make use of this and get into it from the core.
Prabhu, a simple question is, so how do we get into it? I mean, so are we directly contacting someone, or we go through you, we learn some hands-on or something?
There is a science working group, and if I'm not, I was always thinking Manjari is there. I think Susan, Konar, BCJ, and they are the more, at least the recently active names that I'm able to remember. And there'll be other people, and many of the black belts, if you approach on this subject, may or may not be directing you to, each one will have their own individual problems. They may not worry about huge. That's another thing that happens in the community usually is big black belts never worry on big projects. Okay. And they will be having their own problems to beat with. And if you go behind, there are science groups and community. It's a different theme, different thinking. And that community, you have to catch up and be part of it. And more importantly, I've also seen, Maura will tell SIGPROC and other experiences. When you develop very good algorithms, don't keep it yourself, put it in an archive, make it available to the public, take feedback and maintain it. Okay. There's no way a very good algorithm in one person's hand is going to be useful. I've seen this from GMRT times, 35 years ago when we built GMRT, many codes, and UTI, MWA, now SKA. Okay. And again and again, the people who wrote this, Willem and all these people, they are now on the timing, they're building the real-time systems. So your own codes, value them, put them in the archive, make it public, give visibility, write a paper if required. Okay, I think that's another thing that I'm telling. It's not just instrument, it's also the software. Okay. Yeah, the future telescopes are going to be only software telescopes. There will not be moving parts in the low frequency telescope, and we'll have, but most of the operations are done software.
Okay, any other questions? Yeah, okay, maybe last.
Yeah, so it was a good discussion. So thanks, Prabhu and Mara and Gopu. So we can break for lunch and we can discuss more probably how to join there. And yeah, you can people. It would be good if Balchandra Dashman, they could also come here, but yeah, we have to think how we can participate more. Okay, so let us go for lunch.
And I don't know, it's just informed. So online participants, you are now breaking for lunch. So thank you all for staying. So I think we'll be back at 2:30, right? Yeah, 2:30 is. So Golam will be the first speaker after lunch.
Speaker from European, next speaker we will have from European pulsar timing array. He will be online. Actually, he wanted to come in person, but could not. So please let us come back.